Hi students, I am here again. Am I live? Am I audible? Let me know in the chat box. Are you back? Are you guys back after the long session of DNF block where we completed each and everything? Right now, we are going to complete coordination compounds. But first, let me know if I'm live, if I'm audible, if you can hear me clearly. I know. Hi, good evening, little boy. Good evening, good evening, good evening. Hi. Let call you all your friends and also call everybody. We are back again. We're live again on this channel. ठीक है. Let me know in the chat box. Please show me some love so that I'm also excited for this session and I could take this session with the utmost energy that is required for your NEET preparation. Hi. Hi, Sanvi. Hi, Sarath. Sarath is back. Sarath has been studying for the past 3 hours. Hi, Sarath. Hi, Sarath. ठीक है. मेरी okay, can you hear me clearly? Is the voice clear? ठीक है. Let me know. Hi, Neha. Hi, Binod. Ravindra. Hi. Okay. Visible, audible, perfect. So today in this session, let me introduce this session to you guys. What can you expect out of this session? So we are preparing for NEET 2024. Coordination compounds. Let me know in the chat box first of all, how do you find this chapter? Is this chapter easy for you guys or is it difficult for you people? Let me know. Hi. Clear, perfect. Let me know in the chat box, how do you find this chapter? And actually, most of the feedback that I get regarding this chapter is, ma'am, we have read all the theory of the chapter and we have solved all the NCERT questions. But still, when I go to attempt the NEET questions or the NEET PYQs, I do not understand how to approach them or I am not able to solve them, right? Is this the main problem even with you people with this particular chapter, coordination compounds? Nomenclature is easy, okay. Pavadharini is saying that she finds nomenclature easy. Neha is saying she finds this chapter very, very easy. Bacha, next time I'll use the board. Today it's not available. Otherwise, I also love teaching on board. Uh, for me, the chapter feels easy to study but hard to remember and recall. Correct, Sanvi? That is the problem with most of the students regarding this chapter, that you are unable to solve the questions because so many concepts just at once that you cannot recall most of them when it is required, right? So I have compiled all the questions right now. Okay? Before the questions, we're going to go for the theory. And how I teach you theory is you'll never forget another concept in your life, because I've taught this to JE students. I've taught this like to many JE students. Okay, and I've gotten that feedback, and that's why I'm so confident about this chapter, even for the NEET students right now. Isomerism is difficult. No, I'm gonna teach you isomerism. You're gonna find it extremely easy because very easy questions comes from isomerism. Okay? Yes, even I feel the same. That's the easiest chapter. You just need to know the basics about this. I agree with you, LMSA. ठीक है, chalo, let us start. But before we start, I again want to remind you guys that if you are extremely sincere about your NEET 2024 preparation for the exam that is on 5th May, then you can join this online crash course and you can take it sitting at your home. And what are the benefits of it? That you will be able to be in a schedule, right? When you attend a YouTube session, what happens that you are not bound to a schedule. You can sometimes attend the class or not attend the class, and you do not have tests that happen that are all India wise, and hence you do not know where you stand in your class, right? That thing happens, correct? Beta, this lecture is going to be 2 to 2.5 hours long because I'm going to cover each and everything about this session. But I'm again going to remind you that if you're sincere about your preparation, then you can join this crash course. The link is in the description box below. You have to do nothing. Just go and sign up on the link down below and you will get contacted about the course. Okay. I've told you about the length of the lecture. Now start with the very first topic that is always asked in your NEET exam, and I will tell you with proofs that these little things are even asked in your NEET exam. So the number first thing that is on your screen is the difference between the double salt and the coordination or complex compound. This kind of question comes every year. Okay? So what you need to know, what is a double salt? Something, when you put it in water, it ionizes 100%. So 100% ionization occur, then those substances are called double salts. For example, in carnallite. The next important thing is that you must know the name as well as the molecular formula of all the double salts, because these are every year asked in exam. I'm going to show you with example. Can you see this question? Which of the following forms a set of complex and a double salt respectively? This is NEET 2023 Manipur question. Can everybody see? So I'm telling you in NEET 2023, 2022, 2021, these kind of questions are asked, and sometimes even their names have been asked. So please focus on the name. Carnallite, the name and the molecular formula is KCl.MgCl2.6H2O. Mohr salt, which is a double salt, which is FeSO4.NH4 whole twice SO4.6H2O, and potash alum or just alum, it is K2SO4.Al2SO4 whole twice dot 24H2O. So you need to remember all these formulas with their names. What happens in a double salt? If I put any of the double salt in water, I will get each ion separately. For example, K plus I'll get separately. For example, Mg2 plus I'll get separately. For example, Cl minus I'll get separately. For example, Fe2 plus I'll get separately. Right? So these kind of ions I will get in water, and everything will be 100% ionized. But what happens in a complex compound? They will be visible in square brackets first of all, most of the times. Okay, and they will be visible just like this. But what happens in complex compounds, bacha? Only the counter ion. They can be a cation or a anion. Can you see? This chlorine is a anion, right? And this potassium here is a cation, right? So only and only these counterparts ionize in water. Remember this thing, extremely important. Only these ionize in water, while the double salt entirely gets ionized. Okay? Yes, bacha, this is from scratch. This is from the very basics. Even if you know nothing about this chapter, you're going to learn everything just today. Okay? Next, everybody understood the difference between double salt and coordination complexes. Now we're going to solve one question from the NEET 2023. Who can answer this question? I'm again looking at the chat box. What do you think should be the right answer to this? What do you think should be the right answer to this? Which of the following forms a set of complex and a double salt respectively? What should be the answer to this question? NEET 2023 question. Yes. Yes. Let me know. What should be the answer to this question? I'm looking at the chat box. Nobody is replying to me yet. Ma'am, please repeat. But just the question is on the board right now. What should I repeat for you? What should I repeat? C. Sanvi, Kavya is saying A. And Sham is saying C. Okay. And the correct answer is actually Bacha C. You both are correct, Sanvi and Sham. And even Sarveshwaran has given the right answer. And Soumya and PCLMSA, you're not correct. But just CuSO4.5H2O is can be considered a complex, but this is not a double salt. This is not a double salt, right? So A option is cancelled. The only correct option is that the first is the complex and the next one is the potash alum double salt, right? This is potash alum double salt, and this one is your complex compound, which I can write just like this. K2 will be here, right? Platinum will come here, and then it will be NH3, which are twice NH3 and Cl2. This will be the complex form. So this seems to be the right answer. Everybody understood? Very good, Susi. Very good, Anil. Correct answer, Kamlesh and Cosmo Sapien. Okay. Most of the people have given correct answer. Let's move forward. Now, what are coordination compounds? Now, we have seen the very basic thing, which is a difference between a double salt and a coordination compound, right? So double salt is something which 100% ionized in water, but in the coordination compound, only the counter ions ionize in water. Now, what is a coordination compound, madam? So the definition that most of you are aware of is what? When transition metal forms a complex with something, they form a coordination compound. But this is a wrong statement. What is the right statement? The right statement is whenever any metal, okay, which has a what? Which has a vacant d orbital or vacant orbital, just vacant orbital. Mostly it is d orbital, so I'm going to write d. So whenever any metal which has a vacant d orbital, it can be any metal whatsoever, and that metal is when it is surrounded by bacha, what? Any non-metal is called a coordination compound. This is the only correct definition of coordination compound. Whenever any metal is surrounded by non-metals and the bonding between them is the coordinate bond, that kind of compound is called a coordination compound. Now you will ask me, ma'am, what are metals? What are non-metals? How will I know that? Now let us look at the another category of the periodic table, which is this. Can you look at this table? Can you see that 70% of this table is red in color? That red colored thing are actually metals. So not even 70, it is 70 to 75% of the entire periodic table is just made up of metals. So any of these red colored elements which have a vacant d orbital, right, which have a vacant d orbital, when they form a compound with any of these non-metals, which is for example carbon, nitrogen, oxygen, all these blue things are what, bacha? Your non-metals. If they form any complexes with these things, these are called coordination compounds. Easy peasy? Easy peasy for everybody? Okay? Now let's move on to the next thing. For example, look at these two very famous coordination compounds. You will understand what I was trying to say. Can you look at this coordination compound, which is a hemoglobin compound found in our blood, right? It is a coordination compound of iron. What does iron have? Iron is a metal which has a vacant d orbital. Okay? And can you see that it is surrounded by nitrogen? What are nitrogen? Nitrogens are non-metals, right? And it is surrounded and it is forming a ring-like structure, right? And hence it is definitely a coordination compound. Similarly, the next example here is of chlorophyll that is found in the leaves of plants. But can you see the metal here I've used is not a transition metal, but it is a S block element, right? Magnesium is a S block element. But again, magnesium, because it has d orbitals, it can behave as a coordination compound. Can you see that it is again surrounded by non-metals, that is nitrogen, hence Pakka, for sure, this is also a coordination compound because it is satisfying the condition that in the middle will be a metal surrounded by non-metals. That compound will be called a coordination compound. Okay? It is satisfying all those conditions. Yes, cobalt in B12, again a very good example of coordination compound. You are absolutely right. Absolutely right. Okay? Hanji? Ha. The dash line present, it is away from the user, and the wedge line present, it is towards you. Okay? Away you and towards you. Okay? Now let's move forward to the next thing. Now we're talking about what kind of bonding is present in coordination compound. Okay? So what kind of bonding is there? Let me change the pen color so that it's visible even more. So what all bonding you have already studied, just let me know about that. I think that you've studied number first is about your ionic bond. Okay? Everybody is studying about ionic bond. What happens in ionic bond? For example, here is a sodium. Okay? Sodium has a 1 valence electron, and for example, it wants to make compound with chlorine. So what will happen? Chlorine has 7 valence electrons, right? Like this. Now what will happen? What will be the next thing? That this 1 electron from sodium will actually get completely transferred towards chlorine, and the end product will be what? It will be a Na plus as well as a Cl minus ion. This is how a ionic bond is formed, correct? a complete transfer of electron happen in ionic bond, right? Complete transfer, I'm writing it here, complete transfer of electron happens here, correct? Now what is the next kind of bond? The next kind of bond is a covalent bond, which you have studied, and you know how covalent bond is formed by sharing of electrons, isn't it? By sharing of electrons. The most famous example of a covalent bond is what? CH4, isn't it? So how CH4 is formed? Carbon has 4 electrons in its valence shell, and the 4 hydrogens bring one electrons, right, like this, and then 4 coordinate bonds are formed. Each atom, can you see, each atom, that is carbon and each hydrogen, brings one electron of itself and form a sharing of bond, which is called a covalent bond. The other kind of bond that is used in coordination compounds is called the coordinate bond. What is called coordinate bond that we are going to study in this chapter? So what happens in coordinate bond? Now look at this very carefully. In coordinate bond, for example, there is a species A which has a lone pair of electrons. Okay? And then there is a species B which has a vacant orbital. It doesn't have any electrons. So what will happen? This species A, because it is electron rich, it is called a Lewis base. What it is called? A Lewis base. And similarly, species B, which is electron deficient, it doesn't have any electrons, it has a vacant orbital, it is called a Lewis acid. So how will they form a bond now? So they will form a bond when A will completely transfer its electron to B and form a coordinate bond A to B, just like this. So this is how a coordinate bond is formed. Now you'll ask me, ma'am, what is the difference between a covalent and a coordinate bond now? So can you see that in covalent, each atom was bringing its own one electron and sharing the electrons between each other. Like carbon brought its own electron, hydrogen brought its own electron, and they shared and form a bond. But here in coordinate bond, it is again sharing bond. But the sharing here the sharing of electrons in covalent was even sharing. But in coordinate bond, sharing bacha of electrons is uneven. Can you see? Only and only A is donating both of the electron to the B. The sharing here is uneven. Even though it is a sharing bond, but only one atom is sharing both the electrons to form a bond. And the thing that you should know is one bond is formed by 2 electrons, right? This thing everybody is aware about, that one bond is formed by 2 bonds, 2 electrons, correct? Okay? So this you must know. So Lewis base and Lewis acid kind of concept is used and a coordinate bond is formed in this manner. So everybody now know what coordinate bond is. Okay? It is uneven sharing of electrons from one species to the other species. Everybody understood? Yes, it is mutual sharing in covalent. Absolutely right. Now there is another kind of bonding which is sometimes asked in your exams. That is called a synergic bond. Synergic bond. So right now, what did I tell you? In a synergic bond, for example, the ligand, the donor atom that we are using is called a CO atom, which is called a carbon monoxide ligand I am using. Okay, for example, this is my metal atom, okay, and here it is the carbon monoxide ligand. Okay, so anything. So what is ligand now, you might ask me? So ligand bachcha is anything which was donating the electron. For example, here A was donating. So A becomes the ligand which is electron rich, which donate the electron. Donate electron is called the ligand, right? And it donates the electron to bachcha what? It donates the electrons to the central metal atom. This is called the central metal atom, which has a what? Which has a vacant d orbital. This is a very necessary condition to form any coordination compound, any coordinate bond. Okay, so here what is synergic bonding now? It mainly happens in the species called metal carbonyls. The structure of carbonyls is there is a C triple bonded to O. Now you might ask me, ma'am, who is the donor atom in carbonyl? So, bacha, I'm going to tell you very interesting fact that here the donor atom is not oxygen. Even though you might think, ma'am, oxygen usually has the lone pair of electrons, so oxygen must be the donor atom. No, in this structure of carbonyl, the donor atom is actually the carbon part which donates its electron to the metal. Okay, it has donated, and this bond that we have formed here is what bond, bacha? This is the coordinate bond which I just told you about, right? This is the coordinate bond formed. But what happens sometimes, this carbon also has vacant p orbital. What does it have? It has vacant p orbital. Okay? Now, sometimes what happens, this metal atom sometimes has filled d orbitals. Okay? Sometimes it has, bacha, what? It has filled d orbitals. What does it mean? It means that the metal atom has its own electrons in some of the d orbitals, and what can it do? It can donate these electrons back to the ligand. Okay? Now this bond which is formed by donating the electrons from the metal to the ligand. Okay? Here what is happening? Now metal to ligand bond that is forming. Metal is giving electrons to the ligand. This bond is called, bacha, synergic bond. Does anyone have any doubt in it? So hence, because this is accepting, this ligand which is carbonyl ligand is accepting electrons, is now called your pi acceptor ligand. What it is called? Pi acceptor ligand, because it is accepting the electrons from the metal atom. Everybody understood this? Yes. Okay. Now let's move on to the next thing. This is how a very good diagram of synergic bonding is formed. Can you see that the metal is transferring electrons? This is metal, right? This is the metal. This is your ligand, that is the carbonyl. And this is transferring the electrons to the pi star orbital of the metal carbonyl. And you all know that pi star is what kind of orbital? It is the anti-bonding orbital, right? It is the anti-bonding orbital where you are transferring the electrons back to the carbonyl. Correct? Yes, pi acceptor ligand. Okay, you are giving it to the anti-bonding orbital, and because you're giving it to the anti-bonding orbital, what does anti-bonding orbital do, bacha? The anti-bonding orbital decreases the bond order. You remember bond order from your which chapter? Chemical bonding. You remember bond order? So because it is going into the anti-bonding of the carbonyl, it decreases bond order of your carbonyl. Because here carbonyl had how many bonds? Here the bond order was 3. Now it is decreasing the bond order. It means it is decreasing from 3 to some other value. Hence, if the bond order decreases from triple bond, if you are forming a double bond, means what? From triple bond, you are forming a double bond. It means you are also decreasing the bond strength of the carbonyl, right? You're decreasing the bond strength and increasing the bond length of what? Of your carbonyl. Okay? Of your carbonyl. Everybody understood this thing? I might move around for you to see everything. Okay? Everybody understood this part? Yes, correct, correct. So these are called pi acid ligands. Such ligands which take electrons from the metal atom into itself are called either pi acid ligands or pi acceptor ligands. It is again written over here, pi acid or pi acceptor ligands. The example other than carbonyl are CN, NO, PF3, PR3, C2H4, C2H2, CO2, etc. But the only example you have to remember is just the carbonyl. That is it. Only carbonyl questions are asked in exam. So I won't request you, or I won't tell you to go and learn about the other examples because only carbon is asked in exam. Okay? Next, synergic bonding. After we have read about the synergic bonding, another important thing which nobody will ever teach you, but they come in exams so many times. They have come in exam, and this time there is a very high chance of organometallic compounds to actually come in exam. This is again not given in your NCERT, not NCERT. Okay, but these are asked, these have been asked in your NEET, and please do them because these kind of questions after the reduced syllabus were very common in the JEE 2024 exam. So there is high probability to be asked in NEET 2024 as well. You will thank me when you have learned these concepts after you have taken the exam on May 5. I am again telling you, do not miss this topic. So what are organometallic compounds? So whenever we make a compound between a metal and a carbon. So whenever a compound is made, a bond is made between any metal and carbon is called an organometallic compound. Simple, simple. Okay? The most common organometallic compound you are aware of is your Grignard reagent. Everybody remember what is Grignard reagent? It is RMGX, right? Here what is happening? A direct bond, a direct covalent bond is forming between your alkyl group and your magnesium, which is a metal. So this is a very good example of organometallic compound. What is organometallic compound? Whenever carbon and a metal form a bond together are called organometallic. These are of various types. Every type and every structure is important. Listen to me very carefully. So sigma bonded complexes. What are they? So whenever, for example, here just straight away look at the structure, the theory, you can go later on see the PDF in the Telegram channel. Right now look at this structure. Can you see? There is a metal atom, lead. Lead is connected with 4 carbon atoms, 1, 2, 3, 4. But it is connected through which bonds? Just single bonds. Can you see? And we know that single bonds are what? Sigma bonds. So therefore, these kind of complexes, these are called sigma bonded complexes, sigma bonded organometallic complexes. Easy peasy, simple. Everybody is understanding? Okay, everybody is understanding this. Now what? Somebody is calling me Black Widow. Okay, I don't know if that's a compliment or not. Okay. Yes, bacha, I can take that chapter, but right now focus on this chapter. So this single bond that is formed is called a sigma bonded organometallic complex. What are the examples of sigma bonded? Number first example is the Grignard reagent that I just discussed. Very famous example. Another is this example, this example, this example, this example. As you can see, whenever a metal and a carbon has a single bond, it's a sigma bonded organometallic compound. Next is the pi bonded complex. So organometallic second category is a pi bonded complex. Very easy once again. So what is happening here? So there will be a metal atom. Again focus on just the structures. You can read the theory on your own. So this structure has a platinum metal here. Can everybody see? Now this platinum metal is trying to form a bond with this C2H4 complex, which is a ethylene, which is the ethylene compound. So can you see it is forming a bond with not any of the carbon but with this double bond. It is trying to form a bond with the double bond. Okay? So whenever they try to form a bond with any of the pi bonds is called a pi bonded complex. Okay? And how are their name written, bacha? This for example, this is a very famous compound. It is called a ZZ salt. You must know the structure of this salt. Okay? And the structure is there is a potassium ion, there is a PtCl3, and the fourth ligand attached is the ethylene, which is C2H4. And can you see here? Neta2 is written. I will write it clearly. Something like this is written. Neta2. This neta bacha represents, this neta bacha is called the hapticity of the ligand. This neta is called the hapticity. And what is hapticity here? It means how many, it's very easy, how many carbon atoms are attached or how many carbon atoms are bound to the metal. Can you see here only 2 carbon atoms are 1, 2. So here hapticity becomes 2. Now for this iron, this is an example of ferrocene. Can everybody see? So this is example of ferrocene. Here the iron is now bonded to two cyclopentene rings. Cyclopentenyl rings. Okay? Here what will be the hapticity? The hapticity here, can you see that here 1 carbon, 2 carbon, 3 carbon, 4 carbon and 5 carbon. So here the hapticity is because it is attached to 5 carbons. So the hapticity becomes 5, and because there are 2 rings, so we are gonna write outside the bracket number 2. So this is the entire structure of this. The next is this structure, which is chromium is here. It is attached to benzene ring. 2 benzene rings are there. So I am going to write the hapticity here. How many carbon atoms? 1, 2, 3, 4, 5, 6 carbon atoms. So hapticity is 6 benzene, and to the whole twice because 2 benzene rings are there. So this is how pi bonded complexes are found. Everybody understood? It's an easy concept, right? Easy concept, right? Thank you, Khushali. Okay, Khushal, sorry. Okay, everybody understood this concept. Now, another thing, that the last type of organometallic compound is where both bonds are there, which is sigma plus pi bonded complexes. The only kind here is called the metal carbonyl. So metal carbonyls actually forms both sigma plus pi bonded complexes. How? These are again classified into 2 categories. Number first is the monomeric. Why? It has both sigma and pi bond, you might ask. For example, this is the metal and it will form bond with the metal carbonyl, means this kind of compound. Can you see? This carbonyl has a pi bond, and this bond which is formed, it is called the sigma bond. Hence, the metal carbonyl compounds are called sigma plus pi bonded complexes. Okay? These are again of 2 types, which is monomeric. Monomeric means what? That there will be only one single metal atom. Can you see? To one single metal, there will be carbonyls attached. For example, 4 carbonyls are attached in nickel CO4. Here 5 carbonyls are attached. Here 6 carbonyls are attached. And you must know the geometry of each of them. Now the next kind of the sigma plus pi bonded is the polymeric metal carbonyl complex. Polymeric means what? That there will be 2 or more than 2 metal atoms bonded together. Can you see here Mn2CO10? Here 2 manganese are bonded together and the other carbonyls are attached in a manner like this. The carbonyls are attached in what manner, Bacha? In a tetrahedral, in a octahedral manner. Can everybody see? Octahedral manner. To each manganese, there are 1, 2, 3, 4, 5 carbonyls attached in a octahedral manner. Similarly, in the CO2-CO8 complex, this is how the structure will look like. Please concentrate on the structures. Please remember these structures are not too difficult, and no other structure other than mentioned here will ever be asked in your exam. Only these 4 structures can be asked. Okay? And this is the structure of COC, CO2, CO8 compound. Everybody understood? Okay? Next is, now let us return back to the coordination chemistry. Let us return back to the coordination chemistry. Let me turn on the AC. It's really hot here. Okay? If you have any doubts, let me know in the chat box. I'm going to solve all your doubts. Okay? Just like last time. Now, some important terminologies. First of all, you need to know how a coordination compound actually looks like. It looks like that it is enclosed in a square box. Can you see? There will always be a square box, and everything inside the square box is called a coordination sphere. Remember this. Everything inside the square box is called the coordination sphere. These terminologies are important. Questions are asked on these terminologies. Next thing that you should know, that the metal atom here is called the central metal atom, because that will be in the center and the ligands will surround it in its geometry. Okay? And the thing attached to it in brackets is called a ligand. Okay? And the number here outside, the number here outside the ligand is called, bacha, what? Is this the coordination number? Is this the coordination number? Let me know in the chat box. I'm looking at the chat box. I am looking at the chat box. Is this 6 the coordination number? Who can tell me? Is this a coordination number? Yes or no? Yes or no? Yes, ligand will be inside the bracket. Inside the bracket, yes. Is this the coordination number? Yes, yes, Ayush Sharma is correct. This is not the coordination number. Okay? This number represents what, bacha? This number represents number of ligand. Always remember this. Do not get confused that this is the coordination number. And why this is not the coordination number, I'm going to teach you just after a while. This is not the coordination number. If you write that this 6 is the coordination number, you will be entirely wrong. You will do so many questions wrong in your exams. Okay? And what is the oxidation number? Oxidation number will, see, coordination number is of the, again, central metal atom, and oxidation number is again of the central metal atom. Just remember this thing. What is oxidation number? For example, to the central metal atom, there are so many ligands attached. Okay? So when the ligands are attached to me, all these ligands will comprise of the coordination number. Now, if I remove all the ligands on me, when I remove all the ligands, the charge that is on me after removing all the ligands is called the oxidation number. Remember this thing. After removing all the ligands from me, the charge that remains on the metal atom is called the oxidation number. Everybody understood? Okay? Yes. Next, we'll move forward. Before that, can you see that I've written two compounds over here? Number first compound, can you see that here the square bracket is actually on the right hand side? Can you see the square bracket is on the right hand side? So here, this is the cation. The potassium here is the cation. Okay? And here, herefore represent a anionic complex. What does it represent? Anionic complex. You should know the difference between a cationic and an anionic complex. Why? It will be very essential when you will learn about the IUPAC naming, which I'm going to teach you the very easiest way, which you will never again do any mistakes ever in your life. Okay? And why is this the cation? You can either see that if it is on the left side, can you see if it is on the starting of the bracket, we can actually not do right and left, we can actually do that. If it is at the starting, then it is a cation. Okay? And the other way to identify it, if this metal, if the counter ion here, this is called the anything which is outside the bracket. Anything, for example, anything which is outside the square bracket, bacha, is called the counter ion. Remember this. It could be on the starting of the bracket or it even can be on the end of the bracket. Okay? This can also be the counter ion. Okay? Every time when it is on this side of the bracket, it will be a cation. And if it is on this side of the bracket, it will every time be an anion. Always remember this. Okay? The other method to understand whether this is a cation or an anion is if a metal is present over here, it is a cation. For example, look at this complex, the other complex which is just right here. Can you look at this complex? So here, bacha, this one now forms your cationic complex. What this is formed? This forms your cationic complex, and here sulfate forms the anion. Why? Because sulfur is a non-metal. Everybody agrees with me? Because sulfur is a non-metal, sulfate is a non-metal, hence this forms an anion and this forms a cation. You must be very clear about the anionic complex and the cationic complex. Whenever the square bracket is on the anion side, it is the anionic complex. When it is on the cation side, it is the cationic complex. When everything, the square bracket is on the cation side, cationic complex. Everybody understood this? Everybody understood this? Oxidation number is equal to primary valency. Yes, you are right in that, but we're going to come that on later on when I'm going to explain to you everything. Till here, everything is clear, the important terminologies. Let's move forward. The other thing that you should know is what are homoleptic and what are heteroleptic complexes. So, bacha, this is again every time in even 2023, this question again came in your exams. So, what are homoleptic? Whenever a complex, in a complex, when the ligand is same, when it is bound to only one type of donor groups or ligand, Okay, when there is only one kind of ligand, it is called a homoleptic complex. And when it is bound to two different, can you see in the below example, there are two different ligands, 1 and 2. So whenever it is bound to more than one ligands, it is called a heteroleptic complex. Easy, nothing to worry about. And why is this classification important? Why are you teaching basic things, madam? NEET 2023 question on your screen. Homoleptic complex from the following complexes is. Who can answer this question? This is NEET 2023 question. Homoleptic complex was asked. This is asked every year. I didn't even have to search it. In 2023, this question was there. Every year, such kind of questions are asked. Who can answer this? Who can answer this? Who can answer this? Yes, SO4 is a counter ion. Sanvi is correct. Counter ion is anything which is present outside the square bracket. Who can answer this question? I am looking at the chat box. D option, Sham. Sri also is saying D. Preeti is saying C. But kaise? Here there are two. In C there are amine also and aqua also. There are two kind of ligands here. So it is a heteroleptic complex. Amine means NH3, aqua means H2O. Two kind of ligands are there. And everybody else is answering D. Crazy dude. Oh, hi crazy dude. Welcome back. Then Banot Ravindra Kamlesh. Hi everybody. Hi Sefali. Everybody is correct. The answer is D because this has only one kind of ligand which is oxalatoaluminate. Extremely right. This is the homoleptic complex. Correct answer. Yes, you can ask me the doubt. Now the next classification of ligand. The number first classification was homoleptic and heteroleptic. Okay, the next classification of ligands is based on two things. Number one is charge. Number second is denticity. What are each of the things? Charge can be, it can either be a neutral ligand. Neutral ligand means what? What is the function of ligand? First tell me. Ligand is anything that can donate electrons. What is a ligand? I'm writing here that can donate electrons, right? That is the definition of a ligand. So neutral ligands means what? That they will have lone pair of electrons on it, right? Lone pair can be neutral, positive, even positive, positive species can be ligands. Now you ask, ma'am, if it is positive, it is electron deficient, how can it donate? I will tell you with examples. Wait. And if it is negative, obviously, negative means it contains excess of electrons. Definitely it will donate the electrons. Now the next thing is denticity. Denticity means what? Denticity means number of donor atoms. It means what? It means number of donor atoms. What does it mean? It means number of donor atoms. Okay? Now, the donor atoms can vary. It can be number first way to look at density is number of donor atoms, and the second way is to look at how many bonds are forming. This is another great way. If one bond is forming, then monodentate, two bonds are forming, bidentate, tridentate, tetra, penta, hexa. This many kind of denticity can be there. Understood? Now let us look at them one by one. Based on charge, the neutral means they will have excess lone pair of electrons. Okay? So for example, carbonyl, the donating atom is carbon. Remember this, in carbonyl, the donating group is carbon. In NH2, this is what, bacha? This is your ethylene diamine, which is NH2CH2CH2, which is a very, very important ligand. Its short form is En. You must know the structure. So I'm going to teach you the structures of each and every ligand. Extremely important because structures are so many times asked. If you do not know the structures, you will not be able to tell the denticity of the ligands. Okay, because sometimes they give us a typical structure, and till you know how to draw the structure, you won't be able to solve it. Here, how many? So here again, can you see the donor ligands are on the nitrogen? Here nitrogen has lone pair. Here again nitrogen has lone pair, right? So here the donor atoms are the lone pair. So this is a neutral ligand. The next example is water. So water may oxygen has lone pair of electrons. In ammonia, nitrogen has lone pair of electrons. What can be the other example? So the name of amine. So the name you use for the ligands here are written. This is called carbonyl. This is called ethylene diamine. This is called aqua in the IUPAC naming of the coordination compounds. Remember, do not write it water. This is called aqua. This is called amine with a double M. Corrected. Here it will be AMMINE. Other kinds of neutral ligands are NO. NO ligands, which is called your nitrosyl ligands. Nitrosyl ligand, again another kind of neutral ligand. More example I can give you. For example, C5H5N. Right? What is this? This is a pyridine molecule. Pyridine molecule. Pyridine molecule is again a neutral ligand. Okay? Everybody understood this? So what is the structure of pyridine? This is the structure of pyridine. Here the nitrogen will be there. Okay? And here there will be like this. The double bonds will be present. And here the nitrogen is the donor atom. Everybody understood? So these are some of the examples of neutral ligands. None of the ligands will come outside of this. I'm going to discuss each and every ligands that are possible in your exam. Next is a positive ligand. So positive ligand, even though what is happening here, the entire species might have a positive charge on it. For example, hydrazinium has a positive charge on it. But can you see that here the nitrogen contains a lone pair of electrons. So it can donate this lone pair of electrons and form a ligand. Okay? And here again in nitronium ion, again nitrogen has a lone pair of electron. In nitrosonium ion, again nitrogen has a lone pair of electron which it can donate, even though as a whole it has a positive charge, but there will be some of the atoms which have a lone pair of electrons which it can donate. Okay, the other example can be anilinium ion. What can it be? For example, like this. For the positive, I'm again writing anilinium means here it will be NH3 plus. NH3 plus, but here again this has a lone pair of electrons. I can write a positive sign on this. This is again bacha a positive ligand. Everybody understood this? Okay. Next, hydrazinium. Yes, this is again a very important ligand. Hydrazinium. Again important is nitronium and nitrosonium. You must know the difference. Nitronium is NO2 plus. Nitrosonium is NO plus. Okay, remember these little details. Next is negative ligands. Negative means which has excess of electrons or excess of negative charge. For example, chloro. For example, cyno. For example, bromo. Okay, you must know how these are written. These can also be written as chlorido. Okay, both are correct. This can also be written as cynido. This can also be written as bromido. Okay, both are correct. Whatever you want to use, you can use, or whatever is given in your exam. And especially consult NCERT, whatever is written in NCERT. I think it's chloro, cyno, bromo. That's written in NCERT. Okay, then O is oxo, then hydroxo, then carbonato, acetato, thiocyanato, sulfato, oxalato, and nitrito. All these are negative ligands. Okay, everybody understood this? These are all anionic ligands. These are called what, bacha? These are called anionic ligands because they have a negative charge on them. Everybody understood? Okay, clear? Okay, thumbs up. Very good. Please like the session if you haven't liked the session yet. Now, again, I'm going to talk about the next classification, which is based on the denticity. We have classified on the basis of neutral, positive, and negative ligands. Now, on the basis of the denticity. Denticity mein number one is the monodentate. As the name suggests, it has one. Mono means one. So, they have only one donor atom. That is, they provide only one pair of electron to the central metal atom. Okay? They provide only one. That is, they are forming only single bonds. The best thing to remember is, whenever, for example, with a metal, only single bond is forming. For example, with fluorine. For example, with OH. What is happening? Only one bond. If only one coordinate bond is forming, it is called a monodentate ligand. You can also write this thing here. One coordinate bond. This is how I remember. Like one donor atom, again one donor atom, obviously here fluorine, chlorine, bromine, H2O, NH3, Cn, NO2 minus, OH minus, CO, pyridine, H. These are all monodentate ligands. Okay? Next is your bidentate ligand. Bidentate ligands, which means what? That they have two donor atoms. Remember this, two donor atoms will be there and hence they will be forming two bonds. two coordinate bonds will be forming. For example, look at ethylene diamine. This is the structure. Ethylene means what? Ethylene means that there will be a ethyl group. Ethyl means two carbon. Can you see there are two carbon, number one carbon, number two carbon. So ethylene, to ethylene there are two amines attached. So the structure formation is really easy. To a ethyl compound attach two amines, which is NH2 molecules over here. Right, so this is the ethylene diamine compound. Its short form is EN. It is a bidentate compound and the donor atom here are the nitrogen atoms. Okay. Now again the next important example is the oxalate. Its short form is OX. What is the structure of oxalate? It is C double bond OO. It is what, bacha? It is, for example, 2 carboxylic acid. You can write this, right? This is the structure of carboxylic acid joined together. So what I've done, I've just removed this H over here and given it a negative sign. So this is a oxalate. Simple. So this is the oxalate, which is a bidentate ligand. Can you see there are two donor atoms, two oxygen are the donor atoms, two coordinate bonds are forming. Next example is acetyl acetonato. Extremely good example. Acetyl, it means to a acetyl group there is acetone group attached. What is acetyl group? For example, this is the acetyl group. Acetyl has C double bond O. CH3 group is the acetyl. Acetone has this kind of group, acetonato. So this is the formula for acetyl acetonato. It is again a bidentate ligand. The donor atoms are these two oxygens. Remember this. Okay. Again your 2,2-dipyridyl, its short form is DIPY. Here again the donor atoms are 2 nitrogen. Now what is the one thing that you're noticing in each of these bidentate ligand? Again come back to the number first example. Can you see that with the bidentate ligand, here it will be a metal atom that it's donating its electron to. Can you see that with each there is a formation of one ring? Can you see one ring is forming here? Can you see again one ring is forming here? Can you see with bidentate ligands there is a formation of a single ring with the metal atom. Here it will be a metal atom. है ना? Can you see that there is a ring formation here which is extremely important? Extremely important. Let's look at more examples. So these are more examples given here, which is glycinato, carbonato. But can you see, and here again in salicylato, these two can be the donor atoms like this. This is again forming one ring. Ring is forming, and ring is forming. Can everybody see the formation of rings? Okay. Now let's move on to the next class of ligand, which is a tridentate ligand. It means it will have 3 donor atoms. 3 donor atom, it means 3 coordinate bonds will be formed. 3 coordinate bonds will be formed. Everybody is understanding this thing? Hello? ठीक है? 3 coordinate bonds will be formed. And for example, it is diethylene triamine. In tridentate ligand, bacha, what is happening? There is a formation of 2 rings. Can you see one ring, 2 ring? Here again, in a tridentate ligand, there is formation of 1 ring, 2 ring. Can you see 2 rings are forming in a tridentate ligand? I will tell you one interesting phenomenon afterwards. Okay? Now again, in tetradentate, there will be 4 donor atoms, 4 bonds, and the number of rings here will be 3. Number of rings with just one. With one ligand, number of rings with one ligand. Remember this thing? Number of things with one ligand here is actually 3. In tetradentate, the number of rings is just 1 behind. Tetra means 3 rings. Okay? The other example is triethylene tetraamine. Again, triethylene means what? 3 ethylene molecules. Can you see? Number 1 ethylene, number 2 ethylene, number 3 ethylene molecules. And tetraamine means 4 amine molecules. Can you see? This is number 1, number 2, number 3 and number 4 amine molecules are attached. So the structure is very easy if you know the name, or if you know the structure, then you can call out its name. Any way is preferred. Okay? Whatever suits you, you can do that. Now again with pentadentate, the most important example is EDTA -3. It will form how many rings? It will form, bacha, 4 rings. Correct? And similarly your hexadentate is EDTA 4 minus. It will form your 5 rings. Remember this. It will form a 5 ring structure. So can you see as the denticity is increasing? Can you see as denticity denticity. As denticity is increasing, number of rings also increases. Correct? So this is one observation that you have seen. Now how to apply this observation, I will let you know later on. Just remember this thing, that as I was increasing the denticity, the number of rings in the complex were also increasing with just one ligand. Everybody is understanding this? Okay? Now the next thing that we can do, now next kind of ligand is the bacha ambidentate ligand. What is ambidentate? So whenever, what is happening? Whenever in a ligand there is a possibility of two donor atoms. I mean, for example, look at this compound which is a nitrito compound. Okay, look at this cyano compound. So here what can happen? Both carbon and nitrogen can act as donor atoms. But what actually happens is, at one time only one of them donate the electron pairs, even though both have the possibility. So in one ligand, when in just one ligand both have the possibility to donate the electrons, but at one time only one form a coordinate bond, that is called the ambidentate ligand. For example, look at this. This is a nitrito ligand. It is what? This has a structure of NO2. So here both N and oxygen can behave as a donating ligands. So when N behaves as a donating ligand, it is called nitro compound, and when oxygen behaves as a donating ligand in nitro, it is called a nitrito compound. Similarly, in cyano, when carbon behaves as a donating ligand, it is called cyano, and when nitrogen behaves, it's called the isocyano. Similarly, in thiocyanato, which is this kind of ligand, if sulfur is donating, it is called thiocyanato. And when nitrogen is donating ligand, it is called isothiocyanato. So what did I say? There is a possibility of donating electrons from two atoms, but at one time only one atom donates. That is called ambidentate ligand, because both are not donating at the same time, hence it is not bidentate. At one time only one atom is donating and it is formed single bond. It is forming a single coordinate bond. Hence it is called an ambidentate ligand, and such possibility give rise to linkage isomerism. Such kind of isomerism. This is a kind of isomerism only. What is isomerism? When the molecular formula is same but the connectivity is different. Same is happening. Both are NO2 molecules, but here the connectivity is oxygen and here the connectivity is nitrogen. So these are what? Isomers. And this kind of isomerism found in ambidentate ligand is called a linkage, because the linking atom is changing. Hence it is called a linkage isomerism. Clear? Okay. Next I'm going to move forward. So another example of ambidentate is dithioxylate. What it is? It is dithioxylate. Remember this thing. Okay, clear? Clear? Very good, very good. Next is a chelating ligand. What is next, bacha? Next is a chelating ligand. So I just told you that as I was increasing the denticity, the number of rings forming were also increasing, right? So those rings formed by the ligand and the metal atom. Hai na? See, for example, this is the ethylene diamine ligand. It is forming a ring with the platinum. So this ring formed by the ligand and the metal atom is called a chelating ring. This ring is called a bacha chelating ring. And I just told you, as the denticity increases, so it begins when? It begins with two or more donor atoms, right? It begins when the denticity is 2 or more. Okay? So as the denticity increases, the chelation also increases. What is chelation? Chelation is nothing but the formation of rings. I just told you, as the denticity was increasing, tetradentate was forming 3 rings. Bidentate was forming 1 ring. Hexadentate was forming 5 rings with the central metal atom. So those ring formation is called chelation. Okay, so as the denticity increases, chelation increases, and due to chelation, when the chelation increases, the stability of the complex increases very, very much. Remember this thing. The more the number of rings, more will be the stability of the complex. Okay, number one thing. Number second, what are the for example, look at this example, then I'm going to move forward. which is more stable? The number first is nickel DMG complex. Why have I included this example? This is asked so many times in all of the exams, whether it is JEE or NEET exam. Very important example from the exam point of view. Okay. Now the question is, which is more stable? Nickel dimethyl glyoxime complex or copper acetyl acetonato complex. Now, what you have to see number first. You know that, ma'am, I will see, number one thing that I will see is the denticity of both these things. So, whichever will have the higher denticity will form more number of rings and hence will be more stable. This should be your logical answer, right? Okay? So, you must see the denticity first. So, let us see the denticity. So, can you see this is the structure of the first ligand, which is dimethyl glyoxometo. So the structure of this ligand is just like this. There is nitrogen, oxygen present. Now you will ask me, ma'am, this actually has number 1, number 2, number 3, number 4 donor atoms because there are 2 nitrogens and 2 oxygens present. So all of them, these four atoms can donate the electrons, hence its denticity. Your answer will be, ki ma'am, its denticity hence is 4. But this is wrong. So much wrong. Why? Because this is a very, very exceptional case of a ligand. What happens in dimethyl glyoxometo, that only and only the nitrogens act as donor atom. Can you see? Only and only nitrogen act as donor atom, while the oxygens are used to form hydrogen bonding, and hence they do not participate in forming a coordinate bond. Extremely important example from the exam point of view. Please star mark this, very, very important. So this is again what kind of ligand? This is a bidentate ligand, this dimethyl glyoxometo. Now acetyl acetoneto, I just told you the structure. This is again what kind of ligand? This is again a what kind of ligand, bachcha? Acetyl acetoneto is a bidentate ligand. Why? Because it has 2 donor atoms, which is 2 oxygens present on it. Now, how can we decide, ma'am, which both are bidentate? It means both will form 1-1 rings. So, how will I decide which is more stable? Now, I just told you that DMG will form a hydrogen bonding. So, the structures will actually, bachcha, look like this. Can everybody look at these structures? Okay? Yeah, correct. Can't be organic chemistry without exceptions. True that. Okay? So can you look at this structure? Here is the nickel present. Here is the nickel metal present, right? And to this nickel metal atom, what are you looking at? To this nickel metal atom, I just told you because this is a bidentate ligand. So this will form 2 ligands will form 2 rings. This is the number 1 ring. This is the number 2 ring. But can you see, due to hydrogen bonding between the OH, right? Due to the DMG, this hydrogen bonding is formed. Can everybody see? This is the hydrogen bond form here. This is the H bond form here. So hence, due to this H bonding, this actually forms a structure which has number 3 and number 4 rings in total. While the CuACAC2 only forms 1 and 2 rings in total. Hence, this complex is bachcha more stable, which is because this has more rings, more chelation, it means more stability. Everybody understood? This is a very beautiful question. If you have any doubt, just look at it once again, the structure, draw the structure with your hand, and you will understand it much more clearly after you draw it by your hand. Okay? Everybody understood? Okay? Next is the chelating ligands. But what did you not understand about chelate ligand? I am again repeating. Somebody is asking me what is chelating. So, bacha, whenever with a metal atom in the center and the ligand outside is forming a ring-like structure, that ring-like structure formed is called a chelating ring, or that process is called chelation. Okay, simple, easy peasy. So, the chelation, for chelation to happen, there should be at least 2 donor atoms, right? Tabhi to there will be a formation of ring, that 2 donor atoms, for example, nitrogen, will donate its electron to the central metal atom. Hence, the minimum number should be 2. It can be either 3 also. For example, if 3 nitrogen atoms are present, it will form 2 chelating rings. Can you see? Number 1, number 2. So, as the denticity increases, the chelation also increases. Hence, the number of rings increases and the stability also increases. Okay? Now, the next thing is the 5 and the 6 membered rings are more stable. Asterisk this. If you are forming a if there is a complex where you have to describe the stability, which is more stable, which is less stable, then also you can do one more thing is count like how many atoms are there in the ring. If there are 5 or 6 atoms, it means it is more stable than the 4 atom ring. Okay? So it means what? That the 6 atom ring is more stable than 5 atom ring than 4 atom ring. So this should be the order of the ring stability. 6 atom ring are the most stable rings. Okay? Now this is the chelate ring size. Now your next question, ma'am, it can be a 3-membered ring as well. Can you see here that the ligand, for example, donates its electron to the metal atom and it is forming how many membered ring? Can you see this is 1 member, 2 member and 3 member, right? A 3-membered ring is forming. But remember my child, if any time a 3-membered ring is forming, it has so much of strain inside it that it is very, very unstable and it never forms. 3-membered ring never forms. If you are able to form a 3-membered ring, it means your answer is totally wrong. 3-membered ring will never be formed in a chelation ring. For example, a question was again asked in your exam. The question was about the ligand which is hydrazine, which is NH2NH2. Okay? Now, they have asked you that this is hydrazine. What kind of ligand it is? Is it a monodentate ligand or a bidentate ligand? Can anybody answer? In the chart box, I'm looking at the chart box once again. We are back to looking at the chart box. This ligand, NH2NH2, the name of this ligand, bacha, is hydrazine. Can you tell me, is this a monodentate ligand or a bidentate ligand? How many donor atoms do you see here? How many donor atoms do you see here? Who can answer this thing to me? Who can answer this thing to me? Bidentate Sanvi is saying, yes, I just explained it to you. Yeah, like the most common answer people will think because it has 2 nitrogen, ma'am. So this nitrogen also has a lone pair. This nitrogen also has a lone pair. And hence both of these will donate the lone pair to the central metal atom and it will form, and therefore it is a bidentate ligand. But your answer is wrong. This is extremely wrong. It is not a bidentate ligand. Why? Because it is forming an unstable 3-membered ring. I just told you it is very unstable. It is never formed. Hence, hydrazine will always and always only act as a monodentate ligand. Understand this. It will always only act as a monodentate ligand. Okay? Only one of the nitrogen will behave as a donor atom. Okay? Does anyone has, I'm again writing here, this is hydrazine NH2. This will always act as a monodentate ligand because otherwise it forms a 3-membered ring which is bacha unstable. I'm writing it here. It forms an unstable 3-membered ring. Okay? That's why it acts as a monodentate ligand. Hydrazine is a monodentate ligand. Everybody understood? Yes, it can be hydrazinium as well or hydrazine as it is as well. It doesn't matter. It doesn't matter. Okay? Hydrazinium is in any ways a monodentate ligand once again. Now 4-membered ring can be formed, 5-membered ring can be formed and 6-membered ring can be formed. How is 4-membered ring formed? When the ligand itself is of 3 members. Can you see 1, 2, 3 and here the metal atom will come and it is forming a 4-membered ring. 1 member, 2 member, 3 member and 4 member. Okay? So all the other rings are possible. 4, 5, 6. Okay? And the 6-membered rings are more stable than the 5-membered and then the 4-membered. But 3-membered rings are very, very unstable and never form. Everybody understood this? Now let's move on to the next thing. Now I'm going to teach you the IUPAC naming, which is very important, asked every year once again. But before the IUPAC naming, you must know the oxidation number and the coordination number. Okay? So I'm going to teach you a trick about the coordination number. So the thing that you see outside the bracket, I just told you, the thing that you see outside the bracket is not the coordination number. It is what? It is the number of ligands. Okay? It is the number of ligands. Now, how to calculate the coordination number, bacha? To calculate the coordination number, you must do what? You must first write the number of ligands that are mentioned in the question. I have written that. And then multiply it with its denticity. Okay? And then multiply with the denticity. Then the number that you get is your coordination number. Everybody understood this? Now, this number is the coordination number. For example, here Cn. Cn is what kind of ligand? It is a monodentate ligand. है ना? It is a monodentate ligand or an ambidentate ligand. But the denticity here is just 1. Hence, its coordination number is 6 into 1, which is 6. Everybody understood? So, the coordination number is 6. Now, we're talking about the oxidation number. I'm going to write oxidation number over here. So, the oxidation number, how can you calculate? Can you see that outside 4 counter ions of potassium are present? It means what? That this complex will have a -4 charge on it, right? And Cn is what kind of complex? It is a anionic ligand. It means it has a -1 charge on it. And how many Cn are there? 6 Cn. So therefore it will be -1 into 6. Correct? Correct. -1 into 6 plus, I do not know the coordination number of Fe, so I will write plus x. And what is the total charge on the complex? It is -4. I just told you. So it will be equals to -4. So the value of x will come out to be what? This will be -6. It will go here. It will become +6. So it will be +2. So the oxidation number here is 2. Everybody understood this? In the coordination chemistry, we write the oxidation number in Roman numerals. So the 2 will be written as this kind. 2 will be written as 2. The oxidation number is 2. Everybody understood? Easy peasy concept? Yes. The next is this. Who can tell me the coordination number of this compound as well as the oxidation number? Both of the things I want to know. The coordination number as well as the oxidation number. Who can tell me about this? Yes. Yes. Go on. Go on. Let me know. Yes, crazy dude, you are correct about it. What is the coordination number here and the oxidation number here? Again, for the coordination number, the trick is number of ligands. How many ligands can you see? The C2O4 ligand number is 4. What kind of ligand is C2O4? It is called oxalate ligand, right? Oxalate ligand means it is a bidentate ligand, so it will be 4 into 2, right? Plus H2O. How many H2O there are? 2 H2O there. Plus, what is the denticity of H2O? It is 1. It is a monodentate ligand. So, 2 into 1. Hence, the coordination number here comes out to be 4 into 2 is 8 plus 2 is 10. So, the coordination number of thorium here is 10. So, we are calculating coordination number of thorium. It is 10. Now, oxidation number. What is the oxidation number here? Who can tell me? Yes. Yes, coordination number is 10. Very, very good. Banot, your answer is wrong. I hope you understood right now. Crazy dude is correct. Sham is correct. Okay? What is your doubt? Ask me the doubt. Everybody understood this? Now the oxidation number. What is the charge on this ligand? One oxalate has -2 charge, right? And H2O is a neutral ligand. Okay? It is a neutral ligand. The charge on H2O is 0. Okay? So the oxidation number here will be what? Thorium, I don't know, so I'll take X. So it will be, and also there are 4 potassium attached outside. Hence, the charge on the square bracket will be -4. Everybody understood this? Now use this to calculate the oxidation number. The thorium will be X plus C2O4. How many are there? What is the charge on C2O4? It is actually -2. How many are there? 4 into 4 plus H2O is 2. And what is the charge on H2O? It is 0. It is a neutral ligand into 0. And what is the total charge? The total charge is -4 on the square bracket. So the value of X will be what? Who can calculate? People have already said 4, 4, 4. But here in the oxidation number, when you are calculating for the coordination compounds, you will not mention plus or minus because the oxidation number here is written in Roman numerals. So we will not write plus minus, but You must know if it is plus or minus. That is true because this is a metal. So metals will always and always have a positive oxidation number. Remember this. Metals always have a positive oxidation number. Okay. Now what is the answer? It is 4 into 2 is 8 minus 8. Here it will go. So the answer will come 4. So the oxidation number here is a 4 oxidation number. Everybody understood? So now the concept of coordination number. What is coordination number? Ligands into the denticity is the coordination number, not the number written outside the bracket. That is just the number of ligands attached. Okay? This thing is clear to everybody? Yes. Everybody? Okay. Next we'll go on the IUPAC naming part. So how do you name the compounds? So some theory is written over here. You can check it later on when you're going through the PDF. I will just tell you to look at these complex. What kind of complex is this and what kind of complex is the second complex? The first complex, I told you that this one will be what kind of complex? This is a is it a cationic complex or an anionic complex? Who can answer? Who can answer? Number one complex is the anionic complex. Anionic. Why? Because it is present in the anionic part. Similarly, the second complex is the cationic complex. This is the first thing that you should identify while you are writing the IUPAC naming. Okay? 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 Everybody understood this? Now the next thing is what? The next thing while writing the IUPAC naming, the next thing that you should consider is you always write the name of the cation first. What do? You write the name. I'm going to write it here. You write the name of the cation first and then you write the name of the anion. This is the way to write the IUPAC naming of coordination compound. No matter the what anion or what cation is there. And how to write the name of the complex that is in the square bracket. So to name the complex, how do you write it to name the complex? Number first thing, you write the ligands. Okay? You write the ligands and then you write the name of the metal atom. This is how you complete the name. No matter what, if the complex is whether the complex is present as a cation or whether the complex is present as an anion, it doesn't matter. If the complex is, for example, let us look at the option number A. Can everybody see A? So A is a anionic complex. So in anionic complex, I just told you that we have to write the name of the cation first. The cation here is potassium. So I will just write potassium over here. I've written potassium. Okay? So the next thing that I need to do is write the name of the anion. The anion is a complex. So how to begin writing the name of the complex? Write the name of the ligand. The ligand is cyano. How many cyano are there? 6. So it will be potassium hexacyano, right? And because यहाँ पे the metal atom is present as an anion, so its name will change as ferrate. Okay? Now here in bracket, its oxidation number will come. What is oxidation number of iron over here? It is plus 2. Okay? So here I will write ferrate 2. Okay? So ferrate 2, this is the entire name of this complex. Again, let's begin writing the name of the cationic complex. Okay? Yes, correct. Correct, Banot here. Absolutely correct. Absolutely correct. Okay? Now here, what can you write, bacha? In the cationic complex, what is the thing? Write the name of the cation. Cation here is the complex. And how to write the name of the complex? Write the name of the ligand first. Ligand is amine. How many? 4 amines are there. So I'm going to write tetra. I'm going to write tetraamine with double M. Tetraamine. And here I will write simple copper because it is present in the cation part. So whenever the metal is present in the anion part, I will write 8 after it. But in the cation part, I am writing the normal common name of this, which is copper. And here again in bracket, I will write its oxidation number. What is the oxidation number of copper here? Ammonia, amine is a neutral ligand. Here it has a 2 charge. So again copper 2 and here it will be a name of the anion which is sulfate. So this is the entire name. Everybody understood this name? Everybody understood this name? Wow. Somebody is saying, ma'am, what is the structure of meoic acid? And you know what he has written? He has written meoic acid. It is extremely funny. ठीक है. Yes, it's tetra. ठीक है, everybody understood? Easy peasy naming. So first we'll write the name of the cation and then the anion. This is the thing that you need to remember. Now again, this is a very important table that you can consult. So whenever anionic complex are given to you, how will you write the name? Like chromium will become chromate, zinc will become zincate, aluminium will become aluminate, iron will become ferrate, copper will become cuprate, similarly gold will become aurate. So this is a very important table that you can consult so that you can practice more and more nomenclature compounds. And this is again for your practice. You can again go through them. I've already taught you enough of them. Okay? And you can again, whenever I give you the PDF, these are more examples that you can go through. I've taught you enough. Now let's move on to the next rule, which is the EAN rule. EAN rule is what? It is the effective atomic number rule. Sometimes it is asked in exam. Just go through it. It is simple rule. What do you do in this rule, bacha? You just write the atomic number of your metal atom, which is whatever is a central metal atom, right? For example, any complex is given to you. For example, a complex like nickel carbonyl 4 is given to you. This kind of complex is given to you. Okay? So you will write the atomic number of nickel. What is the atomic number of nickel? Sakti va karman fi ko ni. 8. 8. So atomic number of nickel is 28, right? Minus its oxidation number. So, bacha, I'll teach you one another thing. Whenever carbonyl group is there, whenever carbonyl group is attached to any metal, no matter what metal, but the ligand is carbonyl, the oxidation number of the metal will automatically become 0 every time. Any metal atom, so oxidation number here is 0 plus the coordination number into 2. Here the coordination number is what? 4, right? So I will write 4 into 2. So this will be the answer. And if the value that comes after solving here comes out to be, this value comes out to be same as the atomic number of the next noble gas. Can you see it is written over here? If this value, bacha, comes out to be, this value after you have solved this equation comes out to be the atomic number of the next noble gas, then those compounds are extra stable compounds. This is the only meaning behind effective atomic number. How you calculate effective atomic number? According to this rule. And if the answer that comes to you is the atomic number of some natural gas, of some noble gas, then they will be extra stable compounds. For example, they have given chromium carbonyl again. So the chromium, we know oxidation state of chromium here will be 0. Why? Because carbonyl attached to any metal will have a 0 oxidation state. The chromium has an atomic number 24 minus 0 plus 6 into 2, which is the coordination number into 2. So here the answer comes 36. As you know, 36 is the atomic number of the noble gas. Which noble gas is 36 the atomic number of? Let me know in the chat box. I'm drinking water for a few minutes. 36 is the atomic number of which noble gas? Who can tell me? Who can tell me? Who can tell me? Which noble gas? I have not completed isomer yet. We're going to do it just now. I have not completed. Okay? Krypton. Somebody is saying krypton, which is absolutely correct. So this is the noble gas. So I've just given you another very cheat sheet. Like helium, atomic number is 2, 10, 18, 36, 54, 86. So these are the atomic numbers of the noble gases. And if your EN comes to be this, then your compound will be stable. And this bacha order is generally followed only for carbonyl compounds. This rule is true. What I'm saying, this rule is true only for carbonyl compounds. Like it is always true for carbonyl compounds. For other ligands, it might not be true. It might not be that stable. But for carbonyls, this is how we see the stability. If for the carbonyl complexes, if the EN rule comes to be equal to the atomic number of noble gases, those are more stable. ठीक है. Next is Werner theory. Now we are here with the nitty gritty part of the chapter. Now we know right now what coordination compound looks like. We put them in a square bracket. Ma'am, they do not ionize, but they do have counter ions which ionize. ठीक है. They have a central metal atom, they have a ligand, and they have a coordination number, they have an oxidation number. I've taught you all of that, and now you know all of that. Now the question is, ma'am, how do the scientists know all of that? Like, you are teaching us something, it is based on some factual information. So how do the scientists found out about the coordination compound? So we are here on the journey to find out about the coordination compounds. The number first scientist to actually venture into this zone was Werner. Who was he? He was Werner. ठीक है? हाँ जी. So metal in a complex shows two type of valencies, primary and secondary. Remember this thing, metal in a complex shows two type of valencies, primary and secondary valency. ठीक है? ठीक है? This was shown by Werner. Now what are primary valency, what are secondary valencies, I'm going to discuss with you. So can you see this diagram on this screen right now? So what is this diagram actually saying? You've taken a test tube. Okay? In this test tube, what did Werner did? In one test tube, he put 1 mole of COCl3.6NH3. In another, he put COCl3.5NH3. In the other, he put COCl3.4NH3. And the other, he put the same COCl3.4NH3. Okay? Now, what is happening here, bacha? So, what is happening here in this case is, can you see that the chlorine is kept the same? The amount of chlorine, the number of chlorine is not changing, but he is changing the number of the moles of ammonia in each case. Here there are 6 ammonia, 5 ammonia, 4 ammonia, and just like that. Okay? And what he noticed at the end, that with 6 ammonia, 3 moles of AgCl precipitated out. With the 5 ammonia, only 2 moles of AgCl, and with 4 ammonia, only 1 mole of AgCl precipitated out. Okay? After he combined it with AgNO3. So what does it suggest? It suggests that only those compounds which are outside the square bracket can actually ionize and precipitate. For example, what is happening in this case? Number 1, the compound formed was CONH3 whole 6, and then here Cl3 were present. So because 3 Cl3 were present outside the bracket, these were the counter ions, these were the ionizable ions, these ionized as 3 moles of AgCl. Okay? Next, what was the complex form? The complex form was CONH3 and 1 Cl will be there, and here 2 Cl2 will be outside. Now your next question should be from me, ma'am. Ma'am, why are you only writing NH3 first and then you are filling in with chlorine whatever is left? Why am I doing that, bacha? Because always remember, whenever you are forming a coordination complex, the first ligand that will get attached to the central metal atom will be a neutral ligand. First attach all the neutral ligands, then you will attach all the anionic ligands. Remember that. Anionic ligands. First the neutral ligands get attached, then the anionic ligands, because ammonia, amine here is a neutral ligand, so it gets attached first. Now here what will happen? The complex was CONH3, 4 molecules, then 2 molecules of Cl2 come inside and 1 Cl goes outside. Hence this Cl only and only precipitates. So what is the conclusion from this? That only the ions present outside the square box were able to precipitate. It means they were able to ionize in water. The rest, which is inside the square bracket, could not. So he came up with a theory that each metal atom has 2 kinds of valencies. Can you see that this cobalt inside the square bracket is always attaching to 6 atoms? Can you see it is always forming 6 bonds? With here it is attached to 6 ammonia, with here 5 ammonia plus 1 chlorine. Again here 4 plus 2 is 6. So here what is happening? The inside the square bracket that we were calling the coordination number, the coordination number remains the same while the oxidation state keeps on changing. So he figured out that every element, every metal has 2 kinds of valencies, a primary valency and a secondary valency. Let us look at the differences. This is a very important table, very cute table that you can just take. Like it's everything is there here. I'm spoon feeding you everything. You don't have to do any mehnat, any hard work instead of that. Okay? Okay? Next is primary valency. What is the primary valency? The primary valency is same as the oxidation number, which is variable. It can vary. For a metal, it is not same. As we have seen that there are so many oxidation numbers shown by D block elements, variety, variable oxidation number. So therefore, oxidation number is variable, while the secondary valency is similar as the coordination number that I just taught you, and that is non-variable for a metal atom. Okay? And the primary valency is satisfied by anions mostly, but the secondary valencies are satisfied, the ligands, right? The ligands can be neutral, negative, positive, right? So these are satisfied by the ligands. These are ionizable, primary valency. Secondary valency is non-ionizable. It is not directional. Primary valency has no direction, while the secondary valency is direction. It means it has a definite shape, right? Definite shape. I'm going to teach you what shape do they have. They are represented by dotted line structure and they are represented by solid line structure. Always remember this part. Okay, okay. Next, somebody is calling me Krypton, ma'am. Baby, that can be my name. Okay, next theory. So that is the old theory. Werner theory is old. What did Werner say? Werner said that every metal has two kinds of valency, primary and secondary. Primary is also called the oxidation state and which is variable. Secondary is also known as the coordination number, which remains fixed. And coordination number has a specific shape, but the oxidation number does not have a specific shape to it. These are the main takeaway of the Werner theory. Now the next theory that came to explain coordination compounds even better way was the valence bond theory. So what the valence bond theory actually tells us? It tells us, I just told you, how are the coordination complexes formed? That there is a ligand, right? In the coordination complex, there is a ligand and in its orbital, in its molecular or atomic orbital, there is a presence of a lone pair of electron. Can you see lone pair is present over here? And the metal atom has a vacant orbital. So that is the first criteria that I taught you for the coordination compounds to form. So it is based on the same, that the ligand will come with a filled molecular orbital and the metal will have a vacant orbital, and what will happen? They will join both of these atomic orbitals and form a molecular orbital, okay, and form a ligand metal coordinate bond. This is what valence bond theory is about. Extremely easy, right? A filled orbital comes and it mixes with the vacant orbital of metal and forms a ligand metal coordinate bond. That is it. That is the valence bond theory. Okay, and the vacant orbitals of metal should have equal energy. This is another theory thing that you should know. Okay, and this is again key. It utilizes the hybridization of n-1d NSNP or NSNP-ND orbitals of metal atom to yield a set of equivalent energy orbitals of definite geometry such as octahedral, tetrahedral, square planar. If these things you will understand, you have to understand from the chemical bonding chapter, right? If you have read the chemical bonding chapter, you will understand that only those orbitals mix which have the similar energy. They can be n-1d NSNP orbital or NSNP-ND orbital. If they have same energy, they will mix together and form orbitals of equivalent energy which will have a definite shape. That is it, what is written here. Okay, that's the only thing that is written over here. Okay? Yes, Werner is the father of coordination chemistry. Sanvi, you are right. Next thing, valence bond theory. What is the other thing that you should know? In valence bond theory, you learn about two kinds of complexes. Number first is the inner orbital complex. Number second is the outer orbital complex. So what is the inner orbital, outer orbital? I'm going to explain to you right now. For example, this is the d orbital. This is what? This is the inner d orbital. So I'm going to name it as n-1 d orbital. This is your ns orbital. This is your np orbital and this is your nd orbital. Okay? So now what can happen? What can happen is two kinds of mixing can happen. I just told you that orbital mixing happens. So what are the two kinds of mixing? The two kinds of mixing can be for a octahedral complex. Octahedral means what? That 6 ligands will attach, right? 6 ligands will attach. It means I need 6 atomic orbitals for that to happen. So what can be the 6 atomic orbitals? It can be the inner, which is your n-1d, 2 from here, 1 from here, and 3 from here, right? So 1, 2, 3, 4, 5, 6. These can combine together. What am I combining? I'm combining 2 orbitals of n-1d, 1 of ns, and 3 of np together to form a dsp3 or d2sp3 octahedral orbital, which is of equivalent energy, because I've used the d from the inner shell, n-1 shell. That's why these are called inner orbital complexes. Everybody understood? These are called inner orbital complexes. The other possibility is, for example, here again it is n-1d, here it is ns, here it is np, and here it is nd. Now the other possibility is it is actually combining the 1s, 3p, and 2d orbitals of the outer d orbital. So what can be the structure? The 6 orbitals formed now have the hybridization of sp3d2. So because outer d orbital is used in this case, these kind of complexes are called outer orbital complexes. And if you're not understanding anything, you'll understand so much more when we're going to do the examples. Right now, you just need to know these basic things. For example, if the hybridization is D2sp3, it is called the inner orbital complex. If the hybridization is sp3d2, it is called the outer orbital complex. Okay? Yes, very good. These things are clear to you. Now let's move on to the next thing, which is the valence bond theory. The next things that you should know is about the valence bond theory is the coordination number. There are 2 coordination numbers that you're going to study in this chapter that are asked. The questions are formed only from these 2, which is coordination number 6 and 4. You don't need to worry about any other coordination number. Okay, the coordination number 6 has only one kind of shape, which is an octahedral shape, while it can have 2 different kinds of hybridization, which I just told you. It can be sp3d2. sp3d2, it means what? The d is from the outer orbital, hence they are the outer orbital complex. I just told you. Here it can be d2sp3, which means what? Is the inner d that I was using, hence it is the inner orbital complex. Similarly with coordination number 4. Coordination number 4, there are 2 kinds of geometries possible. If the hybridization is sp3, here what you have done, you have used ns and np orbitals, which are outer orbitals. Hence the shape is tetrahedral. As you know, sp3 has what shape? Tetrahedral. The whole organic is based on this. Please do not be confused in this why the shape is tetrahedral sp3. We have done entire organic based on this, right? And hence it is the outer orbital complex. And dsp2, again inner d is used here. Can you see? So the shape here becomes square planar. What is a square planar shape? It is like this. Okay, a square planar shape is formed. It is an inner orbital complex. These are some of the basic things that you should know. What is the inner orbital? What is the outer orbital? When inner d electrons are used, it is when inner d orbitals are used, it is inner orbital complex. When outer d orbital is used, it is outer orbital complex. Easy stuff, right? We're going to practice more examples with which these things will become even more clearer to you. Okay? Next thing. These are some of the limitations of VBT that you can just go through. This is just theory, nothing for me to explain. Okay? Next thing, you can just go through. I will give you in the notes. Next thing is the crystal field theory. So I have told you about 2 theories right now, which is the Werner theory and the VBT. VBT says what? VBT said that the ligand has an atomic orbital which is filled, which combines with the vacant orbital of metal atom, and a molecular orbital of equivalent energy is formed, and the coordinate bond is formed just like that. But crystal field theory actually describes coordination compounds a little bit differently. What it talks about in coordination compounds, bacha, here he talks about that in CFT, he says that the metal atom here, the metal atom is a positive charge and the ligand is a negative point charge. He treats the ligand a ligand which is a negative ligand. A negative ligand he treats as a point charge, and a neutral ligand. And a neutral ligand he treats as a dipole. So what he is saying, that your central metal atom is actually positively point charge, while your ligand is a negative point charge or either a dipole. And hence an interaction between these positive and negative charges happen, and that's how your coordination compounds are formed. So here, according to CFT theory, the interaction, the bonding is totally electrostatic. It is positive and negative charges bonding totally here. It is based upon that. Okay? And crystal field theory mein, this is the thing, he considers ligand either as a negative charge or as a dipole. Correct? And the splitting of the degenerate levels due to the presence of ligands in a definite geometry is called as crystal field splitting, which is extremely important. Like the orbitals get splitted, what happens? I'm going to discuss it again in a while. Right now, just understand that CFT, it treats the metal atom as a positive point charge, ligand as a negative point charge, or a dipole. Next, let's move forward. So before understanding crystal field theory, the thing that you must know are the shapes of the orbitals, the d orbitals. Why? Because on the basis of these shape, if you do not know, you won't be able to understand major concepts out of which questions are formed every year. Okay? Now, Hanji. Hanji. So this is the d orbital. So what is happening? Can you see? I just know that d subshell has how many orbitals? 5 orbitals are there. Right? 5d orbitals are there. Can you see that this orbital is called the dz square orbital? This orbital is called the dx square minus y square orbital. Okay? Here the dz square orbital, the electron cloud. Can you see here? The electron cloud is on the z axis. And here dx square minus y square, the electron cloud is on the x axis and the y axis. Right? So these two are called the Eg orbitals, where the electron cloud is on the axis, right? Is on the axis, the x-axis, y-axis and z-axis. So these two combined, dz square, dx square minus y square, are called the Eg orbital. Okay? The next are these three orbitals that are left, dxy, dyz, dzx. Can you see the electron cloud in all these three orbitals? The electron cloud here is in between the axis. Can everybody see that? Electron cloud is in between the axis. Can everybody see that? Right? Hai na? So here just remember, and this three combined are called T2G orbitals. When we are talking about the octahedral field, I'm going to teach you what is that. Okay? The upper one is called the Eg orbital. The down three ones are called the T2G orbital, where the electron cloud is present in between the axis. In the Eg, the electron cloud is present directly on the axis. Everybody understood this point? Yes, bacha, degenerate orbitals have same energy. Degenerate means similar energy. The meaning of degenerate is equal. ठीक है? Next is, now what happens? Now look at this diagram, extremely important diagram. Now we're talking about crystal field splitting in octahedral complexes. Now that you understand like what kind of d orbitals are there. For example, just look at the above diagram. Here is your metal atom. Any metal atom like your platinum or your iron or your copper is just sitting idly. Okay? So what does this metal atom has? I told you the criteria for a metal atom to form a coordination compound is it should have vacant d orbitals. Can you see that this metal atom has a d orbital, right? Which are all in the same energy. So this is a free metal atom which has a same energy, d orbitals are present. Now what is happening in the second scenario? The ligands start approaching the metal atom. Ligands start to approach. Ligands start to approach. It means what? So this is this metal atom just sitting like it's doing nothing and like just chilling. And suddenly what happened? It realizes, oh my god, there are going to be so many guests in my house today. So its energy increases a little bit, right? Right, like how happens with you? How it happens, like if the guests are about to arrive at your place, what do? You get super hyper. Oh my God, I have to arrange all my house. I have to put things in place. So you become in an active state, right? So here what is happening, as soon as the ligands start approaching the metal atom, they are at the periphery of the metal atom, the energy here increases. Can you see the here energy of the d orbitals increases? Now what is happening? Because we're talking about octahedral complexes. So, bacha, in octahedral, the ligands approach. The ligands, can you see in octahedral, ligands, I'm writing it here, ligands approach along the axis. Ligands approach along the axis. What are the axes? The axes are x-axis, y-axis and z-axis, right? Because the ligands are approaching along the axis. Now again, remember this diagram? Along the axis, the dz square and the dx square y square orbitals are what? The dx square and the dy square orbitals are, the electron cloud is present along the axis. Hence, they will feel most of the repulsion, right? These two orbitals will feel most of the repulsion. Hence, their energy will increase even further. And the other orbitals where the electron cloud is not on the axis but in between the axis, their energy actually goes down, and hence the d orbital split into two, where the Eg orbital goes above and the T2g orbital comes below. Everybody understood this? Okay, right now what the metal has done, the metal was sitting ideally. Now as the ligand started approaching to it, it increased its energy, and then as soon as the ligand approached, because the ligand in octahedral complexes approach along the axis, hence the energy of those orbitals where the electron cloud was along the axis, which is dz square and dx square minus y square, the energy of those orbitals increase and the rest of the orbitals energy decreases, and hence the d orbitals split it. The splitting of orbitals was explained by the crystal field theory. Everybody understood this? Everybody understood this? Okay. Next, now what is happening? What is the ratio of the splitting? So as you know, somewhere in the middle is called the barycenter, where the energy is 0, right? And the increased energy is 3 by 5 and the decreased energy is 2 by 5 delta octahedral energy. The entire energy, bacha, here, because this it has splitting has happened here, this entire energy with the delta octahedral is called the delta octahedral crystal field splitting energy. Remember this thing. The splitting energy is called the delta octahedral crystal field splitting energy, and the above part is 3 by 5 delta octahedral. The below part is 2 by 5 delta octahedral. Everybody understood the splitting? Extremely easy concept if you understand it this way. I'm going to move forward now. Okay? Beta, how the ligand approach? The ligand approach, because now you're trying to react two species together, right? You're trying to react the metal with the ligand, and the ligands always attach themselves in a definite geometry, and that is a octahedral geometry. Okay? Next, crystal field theory. I have explained it to you. All these things. Next thing, what I can tell you is the splitting in the octahedral complexes, which also we have done again. I've explained to you again these things. Let me choose another pen color. You know what I was trying to say? I was saying, let me choose another painkiller. Let me choose another painkiller. That's what I was about to say. Yeah, pen color. Okay. Now, I just told you that this is the energy diagram. And T2G will come below, EG will go above. In octahedral splitting, I'm again and again telling you, because this splitting pattern will change as soon as the shape of the orbital will change. Okay? Now the crystal field splitting energy is the difference of energy between two sets of orbitals. I just told you, right? I told you, right? This energy, this delta is called the crystal field splitting energy, and the formula for calculating this is minus 0.4 N2G plus 0.6 NEG delta octahedral. This is the formula. This is the formula for that. ठीक है? ठीक है? अब N here represents what, bachcha? N here is the number of electrons in T2G, right? And here is the number of electrons in the EG. Now, what is pairing energy? What is the other things? I'm going to teach you one by one. Just wait for me. ठीक है? Now the next thing. Now I told you ki ma'am theek hai, I understood that the splitting has happened. Now what will dictate this splitting? Now because every time same ligands will not approach, different kinds of ligand we just read about. We read about there are monodentate, bidentate, there is amine, there is water, there is cyno, there is CO ligand, carbonyl ligand. So many different types of ligand will be there. Ma'am, will all the ligands cause similar splitting between the EG and the T2G orbital? No, no. Because why? Because why similar splitting will be there? It will not be there. So this splitting actually depends on the type of ligand approaching. For example, if I am a very strong person, then to fight me, you will require more force. And if I am a very 6-year-old little child, will you fight me with the same force that you will fight with a 32-year-old man? Nahi na? So therefore, the splitting actually depends on the kind of ligand that is approaching the metal atom. Okay, the splitting that I'm talking about between the EG and the T2G. So the ligands that dictate the splitting is called the spectrochemical series. Okay, this is the bacha spectrochemical series. It is again extremely easy to remember. You have to know the series because direct questions come from this. They will just give you like few of the ligands and tell you and ask you which is a strong field ligand, which is a weak field ligand, or ask you to put them in order. So these kind of basic questions come. Okay. So here can you see that here the most strong field ligand are your carbon donors. Can you see this is CO, CN. Okay? Carbon donor ligands are those strong field ligands. Then are your nitrogen donor ligands. Nitrogen donor EN is ethylene diamine, amine, EDTA, NCS. All these are nitrogen donor ligands. Okay? And these are your what? Lesser stronger field than carbon donors. Then comes your oxygen donor ligands, for example, H2O, C2O4, OH minus. Then comes your halide donors, fluorine, chlorine, bromine, iodine, and also in between SCN and S2 minus are present. Okay? So this is like a mota upar se order. So carbon donors are the most strong field ligand, then nitrogen, then oxygen, then halide donors. Okay? So this is how the increasing, these are the weak field ligands, these are the strong field ligands. Now what do I mean by that? Strong field ligands, because they are strong, they will cause most splitting. The splitting that was happening, right? They will cause the most splitting, while the weak field ligands, the splitting will be less. The energy difference between the T2G and the EG will be less. That is what is meant by the weak field and the strong field ligand. Okay? For example, look at this example. In the weak field ligand, for example, I just told you, fluorine is a what? Fluorine is a weak field ligand, right? So the splitting between the orbitals will not be that much. Hence, can you see the energy here, energy difference between the EG and the T2G is really less. But in strong field, for example, carbon donor cyno is here. So here the splitting of the orbital is too much, right? Because this is a strong field ligand. Now, the next thing is you have to fill 6 ligands of fluorine. How will you do that? Here, how many electrons of, so let us count the number of electrons of cobalt over here. Cobalt, what is the oxidation state of cobalt in this? Oxidation state here comes out to be +3, right? So here cobalt +3 state. Cobalt +3 means what? How many electrons will be there? 1, 2, 3, 4, 5, 6. It is D6 configuration. Cobalt is D6 configuration. Similarly, here also cobalt is in +3 oxidation state, is D6 configuration. I'm going to teach you how to fill the electrons now. Now, in the very first thing, can you see? Because the fluorine is a weak field ligand. So, what has happened? The splitting is not that much. Okay? The splitting between the T2G and EG is not that much. So, how will the electrons start filling? I have to fill 6 electrons in the d orbitals. I have to fill 6 electrons in the d orbitals of the metal. So, I will fill 1 electron here, 2 electron here, 3 electron here. 4th electron I will fill in the EG, 5th electron here, and 6th electron again here. So how have I filled the electrons? First T2G, EG, then again T2G. So what here what has happened? Because here what is happening, bacha, the delta octahedral energy is very much less than the pairing energy. Pairing means what? Can you see? I've paired the electrons. So this pairing energy is actually more than the octahedral energy in the weak field complexes. Hence, this kind of arrangement is done. But in the strong field ligand like cyno, what is happening? The octahedral energy is not so much. Can you see in strong field ligand? The octahedral energy is so much. Hence, what happens now? How the electrons will fill? One electron will come here, second will come here, third will come here. Now, where will the fourth electron go? The fourth electron can either go here or it can pair over here. But can you see that the fourth electron, to go to the EG orbital, it has to have so much of energy because the gap is too much, right? So because delta octahedral is so much more, hence it gets paired up over here and this kind of complex is formed. Here I can say that the pairing energy is actually less than the octahedral splitting energy for the strong field ligand. This will always be true. So the octahedral splitting is actually less in case of weak field energy and the octahedral splitting energy is more in case of strong field. Hence pairing happens. In strong field, what is happening? Pairing happens, right? And in weak field, pairing doesn't happen. Here pairing happens. Correct? Can you see? First the pairing will happen and after all the electrons are paired up, then only the electrons will go to the EG orbital. Everybody understood this? Weak field does not have pairing. Yes, in weak field does not have pairing because the energy to climb the hill is too less. So the person will do what? Will go and climb the hill. Everybody understood this? Now the next is the spectrochemical series. The series that I just told you about. The carbon donors, oxygen donors, nitrogen donors. That is called the spectrochemical series. And that is always and always determined experimentally. You cannot, there is no other way to know about it. It is experimentally determined and it is based on what, bacha? It is based on the absorption of light by complexes with different ligands. Remember this. It is based on the absorption of light by different complexes and strong field ligand. Can you see the energy difference between the strong field ligand was too much. Hence, they absorb a high energy. Strong field ligands absorb high energy and high energy always have smaller wavelength and weak field ligands absorb the low energy, that is the greater wavelength, and this is the relationship between them. So the splitting energy is directly proportional to the absorption energy of the ligand and it is inversely proportional to the wavelength of the absorbed energy. Everybody understood this? Everybody understood this? Yes. Color of the complexes will be asked. Yes. Yes, but D6 configuration. Somebody wants me to explain the D6 configuration again. So, bacha, the D6 configuration, I'm explaining it again. Somebody told you ki, ma'am, explain this again. So, I'm going to do that again here. So, here, both the cases, what can you see? Cobalt is in +3 oxidation state. Everybody understands that? In +3, the configuration of cobalt is D6, right? So, how to fill the electrons now in the T2G and the EG orbitals? In the weak field ligand, the splitting energy is very low, right? So, how to fill the 6 electrons? First electron will go here, second electron here, third electron here. Now, what about the fourth electron? Should I pair it up or should I send it to the EG orbital? But can you see that octahedral energy is too less? So it can go to the EG orbital. So it's going to do that. It's going to do here because all the electrons are gunda. They just want to roam around freely. Gunda electrons are there, right? Very hooligan electrons. So they're going to take most of the spaces. So it will go here. Fourth electron, fifth electron will go here. Sixth electron now will pair up. What is the conclusion? That the pairing energy is actually more than the octahedral energy in the weak field ligand. Can you see? Octahedral is called the splitting energy between the EG and the T2G. This is called the octahedral energy, right? Which is very, very less than the pairing energy. But in the strong field ligand, which is COCN6, CN is a stronger field ligand. Okay? So, in stronger field has the ability to cause much more splitting. Hai na? It causes so high splitting. The splitting energy is so much more in this strong field ligand. Now, how to fill 6 electrons? First electron here, second electron here, third electron. Now, where to send the fourth electron? Can I send the fourth electron to the Ag orbital? No, because the splitting energy is too high. So what will that electron do? It will actually pair up, and the 6 electrons will fill like this. Hence, the delta octahedral energy is so much more than the pairing energy in the strong field ligand. Therefore, pairing occurs in strong field ligand and weak field ligand. Pairing doesn't occur. Where does pairing occur? In strong field ligand, because the splitting energy is too much. Hence, the electron cannot jump and climb the hill to the Eg. It rather prefers to pair up. Everybody understood? Yes. Very good, Sanvi. Very good. This is again a good point that you brought here. So, bacha, weak field ligands actually forms high spin complexes. High spin complexes. Now, what is meant by high spin? Just be here with me. While the strong field ligands actually form low spin complexes. What is meant by that? Spin is what? The spin of the electron. Now, focus on this spin. On the strong field ligand spin. Focus on, bacha, this spin. Can you see if this spin is plus half, the other spin is minus half, right? If the upward spin is plus half, the downward spin is minus half, right? So, in the strong field ligand, all the plus half, minus half, plus half, minus half actually cancels each other out. Hence, it forms a low spin complex, right? But in the weak field, what is happening? There are so many positive here 4 positive, 4 plus half are there. Hence, it actually forms a high spin complex. This is true always. Weak field ligands will always form a high spin complex, and strong field ligands will always form a low spin complex. Is this funda clear to everybody? Is this funda clear to everybody? Understood? Understood? Very good. Okay? High spin, low spin, and also I'm going to tell you another thing. The another thing is the magnetism. Can you see that in the weak field ligand, the pairing doesn't occur? If the pairing doesn't occur, it means most of the complexes here will be paramagnetic, right? And in the strong field ligand, because the pairing occurs, because the pairing is happening, hence they will mostly form diamagnetic complexes, right? Because all the electrons are paired up here. So they have high probability of forming diamagnetic complexes, while the weak field ligands form paramagnetic because pairing doesn't occur. Hence, unpaired electrons will be more in the weak field ligands. Everybody understood it? These are some of the inferences that you can conclude from all these things which we have. Clear. Next. Okay? Now, I told you this again with the weak field ligand. For example, here we are talking about weak field ligand. Here we are talking about strong field ligand. I'm going to talk again about your D6 complex, or should we talk about another? Let's example talk about the D5 complex. Here also D5 complex. Let's talk about how to arrange the electrons. In D5 complex, in the presence of weak field, how will the arrangement of atoms happen? How will the arrangement of electrons happen? D5, weak field, means what? This energy is too low, right? For the weak field, octahedral energy is very less than the pairing energy, correct? So this is the case with the weak field ligand. So how will I fill the D5 here? The D5 will be 1 electron here, 2 here, 3 here, and the 4th electron will actually go to the Eg and 5th electron will go here. Everybody understood this? But again, the same D5 with the strong field ligand. Strong field will happen. What happens in strong field? That the delta octahedral is so much more than the pairing energy, right? Is so much more, hence the electrons prefer to pair up. So how will the 5 electrons fill in strong field ligands? 1 electron, 2 electron, 3 electron. Then 4th electron will pair up and 5th electron again pairs up. So this is how weak field and strong field ligands will fill up the complexes. Everybody understood this part? So this will be a high spin complex and this will be a low spin complex because most of the electrons are paired up in strong field, hence they form a low spin complex, and the weak field forms a high spin complex. Is this thing clear to you guys? Everything is clear? ठीक है, but हाँ, that happens with this chapter. I understand, Jagnesh, but are you recalling everything? Is everything fresh right now in your head? ठीक है, yes, yes, yes. ठीक है, next. Bacha, color we're going to discuss right now, and how to tell the colors. I'm also going to teach you. So we have done about crystal field splitting. Now the energy, the splitting that was happening between the two orbitals, the EG and the T2G, actually depends on what all things. They depend on the nature of ligand. I just told you, right? If it is strong field ligand, there will be more splitting. If it is a weak field ligand, less splitting. And more splitting means the energy, splitting energy, the delta octahedral energy is so much more than the pairing energy. And here the pairing energy is so much more. Here the electrons will pair up, here the electrons will not pair up. This is just a summary of what we have learned up till now. Okay? Now next, I again come back to the valence bond theory, because sometimes questions can be asked from the valence bond theory. We have just completed the crystal field theory. We are back to the previous theory, which is the valence bond theory. That there also I told you that sometimes high spin complexes will be formed and sometimes low spin complexes will be formed. And what I meant by that. So I always keep it later on, so that right now you have so much more idea about the ligands, about the filling up of orbitals. So now VBT you will understand even much more clearly. Okay, what do I mean by that, bacha? I mean, in VBT, you will actually be given either the either that the complex is diamagnetic, or what is either the magnetism of the complex will be given, or something else would be given about the compound, the coordination number or anything, or the hybridization will be given. Okay? For example, in this compound, the cobalt is in +3 state. There are D6, we have to fill the electrons. Okay? Can you see it is a diamagnetic complex? Diamagnetic means what? That all the electrons are paired up. It means that only, right? That all electrons are paired up. So I'm going to arrange D6 here, cobalt 3D6 over here. It's going to be 1 electron, 2 electron, 3 electron, 4 electron, 5 electron. It is 3D orbital, and it is the 6th electron over here. Now, but it has said, because all the electrons are now paired up. Paired up means what? I can pair this electron with this, this electron with this. So I'm going to do this again. This is 3D orbital. This is 1 electron. I've paired up this electron and I've paired up the another electron. Is this thing clear to you guys? I have filled the 6 electrons after pairing up in this manner, because in question it was mentioned that this complex is diamagnetic, which means all the electrons are paired up. Now it has asked you what will be the hybridization of the complex. What will be the hybridization of the complex form? Who can tell me? Who can tell me? Now what will happen? There are 6 NH3 that I have to incorporate. Every NH3 will bring its electron. So 1 NH3 will come here, 2 NH3, 3 NH3, 4 NH3, 5 NH3 and 6 NH3. So can you see? The hybridization of this complex will be D2sp3. Which means what? Which means this is a inner orbital complex, because inner D is used, right? Inner orbital complex, and hence inner orbital complex, can you see everything is paired up? Hence inner orbital complex will always be low spin complex. Remember this, low spin complex as well as diamagnetic. These are all the things that you can infer out of this. Have you understood this diagram? This is the VBT diagram. VBT diagram, we show VBT like this. The inner orbital complexes are shown like this. In CFT, what I was doing, I was splitting the EG and T2G and then forming the high spin and the low spin complexes. But the inner orbital and the outer orbital, the best example to learn from is actually the VBT. VBT. Everybody understood this? Everybody understood this? Okay, cool. Next example is your FeF6. And they have mentioned, bacha, that it is paramagnetic. Here iron is in +2 oxidation state, which means that here 3d6 is its electronic configuration. Now how will you fill the electrons? Let's fill the electrons with me. Here it will be 1 electron, 2 electron, 3 electron, 4 electron, 5 electron and the 6 electron will come here. Now it has told you that it is a paramagnetic complex, and we also know that F is a weak field ligand, hence it will cause no pairing of electrons. We know that now it will cause no pairing of electrons, right? So right now, where will the fluorines attack? So the fluorines will attack, 6 fluorines will attack. One fluorine will come in S, then second fluorine, third fluorine, fourth fluorine, fifth fluorine, and sixth fluorine. So this is going to be the hybridization of the complex, which is sp3d2. So this is the hybridization of this complex, and because outer d orbital is used, 4d is used, hence it is called the outer orbital complex. And all the outer orbital complex will always be, can you see the spin here? Positive spin, positive spin, positive spin, positive half spin, right? So outer orbital complexes will always be high spin complex. What kind of complex they are? High spin complex, because there are too many, because the electrons are not paired up, right? If they are not paired up, the spins will not cancel out, plus half and minus half will not cancel out. Instead, they will add up, and hence they will be a high spin complex, and mostly they will be paramagnetic. Are all these things clear to you guys? This is what valence bond theory is all about. ठीक है? ठीक है? Very good, very good. Let's move on to the next thing. ठीक है? Next is, so these are all the things I discussed, that inner orbital complexes will be low spin, diamagnetic or less paramagnetic, and outer orbital will be high spin and paramagnetic complexes. ठीक है? So this is the valence bond theory that I discussed with you. The other valence bond theory is called the D-line theory. The D-line is that if I start from D0, D1, D2 and D3, है ना, till D1, D2 and D3, what will happen, bachcha? In these three cases, what happens? These always and always form inner orbital complex. Remember this, ठीक है? Then comes your D4, then comes your D5, then comes your D6, right? Then comes your D7, then comes your D8, D9 and D9, and here it will come your D10. Okay? And from D7 to D10 will always form outer orbital complex, and D4 to D6, in order to decide whether will they form inner orbital or outer orbital, they will depend on the type of ligand attached to it. Okay? So in order to suggest whether they will form inner orbital or outer orbital complex, this is like a common shortcut trick for you guys. D7 to D10 will always form outer orbital complexes, and D0 to D3 will always form inner orbital complexes. But for D4, D5, D6, you need to check it with the ligand, what is the magnetism, then only you can predict whether they can form inner orbital or outer orbital complexes. Is this thing clear to you guys? Is this thing clear to you guys? Okay? Now let's move on to the next. Next thing that you can predict using all these things is the spin magnetic moment. What is a spin magnetic moment, bacha? ठीक है? What is a spin magnetic moment? It is mu is equals to n plus 2 Bohr magneton. N is the number of unpaired electrons. This is how you can calculate the magnetic moment. As the number of unpaired electrons increases, the magnetic moment also increases. For the d orbitals, the maximum number of electrons can be, unpaired electrons can be 5, right? So these are all the unpaired electrons and the possible magnetic moment that is present right in front of them. Can you see these possible magnetic moment? Like for one unpaired electrons, the magnetic moment can be 1.73. For 2, it starts with 2. With 3, it starts with 3. 4 starts with 4. 5 starts with 5. So this is an easier way to just like in your especially MCQ, you can just look at the values and tick mark after knowing what are the number of unpaired electrons. You can just tick mark the correct magnetic moment. Don't need to calculate the root and all. है ना? ठीक है? Next, splitting in tetrahedral field. I was talking about, I just mentioned to you the octahedral field splitting. Now we're talking about the tetrahedral field. In tetrahedral field, what happens in tetrahedral? Tetrahedral shape is for the sp3 hybridization, right? sp3 hybridization has a tetrahedral structure. And what is the structure of tetrahedral? It is somewhat like this, right? It is somewhat like this, where all the bonds, all the atoms, where all the atoms are present in between the axis. Does anyone have any doubt in it? All the atoms, where all the ligands, if the ligands are going to approach in a tetrahedral manner, they're going to approach in between the axis, right? And hence, the electrons which were in between the axis. What were those d orbitals which were in between the axis? They were dxy, dyz, and dzx, right? So their electronic orbitals were in between the axis. Hence, in tetrahedral field, these were called the T2, right? So the T2 orbitals will increase in energy. The T2 orbitals will increase in energy while the E orbitals will decrease in energy. So what will be the structure for T2G? Splitting in tetrahedral actually will look like this. Can everybody see the tetrahedral splitting over here? Okay. So what is happening, bacha? This is your d orbital. Okay. D orbital increases in energy a bit as soon as the ligands start approaching. Now, because it is a tetrahedral splitting, hence the T2 orbitals which were in between the axis, right? The T2 dxy, dxz and dyz, their electrons are present in between the axis. Hence, they will feel most repulsion from the approaching ligands, because right now the ligands are approaching in between the axis. Hence, they will increase in energy and the E will decrease in energy. Again, here the center point is called the barycenter, and some energy T2 energy will increase and E energy will decrease. This is how splitting is done in tetrahedral field. Okay? Easy, simple, just that the splitting order reversed. In octahedral, E was above, and in tetrahedral, T2 is above. Okay? Now the next question should be, ma'am, in the octahedral, you were using the term T2G and EG, while in tetrahedral, you're just using the term T2 and E. Why is that the case? That case is because in the octahedral field, the ligands are approaching very symmetrically. The field is symmetrical. Hence, the word G is used behind it. G means bacha Girard. Girard means degenerate or similar energy. It means symmetrical. Girard means symmetrical, and it is only and only used for the octahedral field. But tetrahedral field is not that symmetrical. Hence, we do not use G over here. We just use E and T2 over here. Everybody understood this? Easy peasy? Beta, I'm doing extremely great right now. Now we're talking about the splitting energy. Now we've learned about two kinds of splitting that happens in the octahedral field and the tetrahedral field. What is happening? The d orbitals are splitting, and the energy between the two splitted orbitals is called the octahedral splitting energy. So what does that energy depends upon? Number one factor is the strength of the ligand. So more will be the strength of the ligand, more will be the splitting energy. I just told you that, right? So it is more in case of strong field rather than weak field. Next is the oxidation state of central metal atom. So when the oxidation state increases, and therefore the CFSE will also increase. What is the meaning of that? See, as the oxidation state increases, for example, if here I am using a PT plus 4 oxidation state over here, for example, okay? So plus 4 means what? It will also have a bacha what? It will also have a smaller size, right? So another inference that you can make is, when the size of the central metal atom is very small, then its CFSE will be very high. Okay, I can here write again one thing, that it directly proportional, it's inversely proportional to the size of, like smaller the size, more will be the energy, size of the central metal atom. Correct? Understood this part? Now let's move on to the second. Next is the transition series. Okay? As soon as the transition series increases, for example, if the element is from the 5D series, for the 5D series, the splitting energy is the most. Hence, for the 5D series, for the 5D and the 4D, all the ligands, remember this thing, all ligands for them, all ligands are strong field ligands. Therefore, in the 5D and for the 4D elements, always bacha, what will happen? Pairing will happen always. Remember this. For 5D and 4D series elements, all ligands will be strong field and always pairing will happen. This is a very, very important observation. And it also depends on the geometry of the ligands. The highest octahedral splitting happens in square planar complexes, then in octahedral, and then in tetrahedral complexes. And this is the variation of that energy. This is how the energy are variate. Okay? Everybody understood? Let's move forward. Color of the coordination compounds. Everybody was just asking me, ma'am, have you done the color of the coordination compounds? How do they show the color? And that's all we're going to study. Actually, I also taught you today in the DNF block session if you attended that class. So what happens, bacha, in the color of coordination complexes? Can you see here that there is an electron present over here? Hannah? And what happens right now in while showing the color, what is happening? The T2G, in T2G, for example, there is an electron. Now, this electron gains some energy and it goes to the Eg orbital. Okay? Now, what will happen? Now, this electron will again come back to its original position, and when it does that, it will lose some energy in the form of light. Right? So, this form of light is what we see as the color of the coordination compound. So what is the number first condition? Number first condition is the orbitals should be splitted. Can you see that the orbitals are splitted? And when do the orbitals split? Therefore, for any compound to show color, for any compound the splitting should be there to show the color, right? Therefore, there should be presence of ligand, right? Because only and only in the presence of some ligand was the splitting of the d orbitals happening, right? If the ligand is not there, all the d orbitals are degenerate and in the same energy state. Therefore, to show the color, there should be some ligand present around it, and hence after the splitting, what happens? If it absorbs an electron, absorbs the energy, it goes upstairs and then it comes down, and when it comes down, it releases energy in the form of light, and that light we actually see. Now, this is actually based on the funda of the complementary colors. For example, the energy that the electron absorbed over here. The complementary colors are like this. This is violet, red, Vibgyor. It is VBGYOR. Can you see that the blue is complementary with orange, the red is complementary with green, the yellow is complementary with violet. Correct? So these are the complementary color. It means what? That if the electron absorbs the violet color, then we will see what? We will see the yellow color, the complementary. Again, if the electron absorbs the blue color, then we will see the orange color. So whatever color it is absorbing, we are seeing the complementary color to it. Okay? Always and always remember that the color of the coordination compounds, number first criteria is there should be presence of a ligand. Number second is that we only see the complementary colors, and through which phenomena we are seeing the color? Through the DD transition. What is DD transition? Can you see? The electron here is going from one of the d orbital. T2G is orbital of what? D orbital, right? EG is again D orbital. So the electron is going from one d orbital to the another d orbital and again coming back to the d orbital. Hence, the transition is happening only amongst the between the d orbital. Hence, it is called the DD transition. Therefore, the color is shown due to DD transition. Everybody understood this? Yes, isomerism we are going to do. I'm not going to leave even one thing today. So this bacha is a table from your NCERT, but this is a better printed table, but the same table is given in your NCERT explaining the concept of the complementary colors. Can you see that this complex COCl absorbed, the color of the light absorbed was yellow, and the color of the coordination entity that we see is actually violet, right? The absorbed color is yellow, but the seen color is violet, means we are seeing the complementary color. I'm going to explain to you another good phenomena that we're observing here. Now we're going to see these structures on the basis of strong field and weak field ligand. Now we know, bacha, what? Now let's compare these two ligands. These two are both cobalt complexes, right? So here in the number, this one complex, The one ligand is ammonia ligand, which is an N donor ligand. The other ligand is a H2O ligand, right? Here one donor is the ammonia ligand, the other donor is a halide ligand. Now we know, bacha, what? We know that the Cl is a weak field ligand, while the H2O is a strong field ligand as compared to Cl, right? As compared to Cl, because we're comparing these two things. Now can you see that the light absorbed by the weak field ligand, is actually 535 nanometer, while by the strong field ligand the wavelength is actually less. It means what? That I just told you that the strong field ligand will absorb higher energy. ठीक है, higher energy means it is inversely proportional to the wavelength. Remember this, inversely proportional to the wavelength, right? So the strong field ligand H2O will absorb higher energy, it means smaller wavelength, while the Cl, which is a weak field ligand, will absorb a lower energy, hence a higher wavelength light. So can you just now compare these things? Now in the similar manner you can compare other things as well. For example, let's compare these two complexes. Here again Cn is a strong field ligand. It means it will absorb stronger energy light. Stronger energy means lower wavelength, but here ammonia is a nitrogen donor ligand. It is a weak field ligand as compared to Cn, hence it will absorb a higher energy wavelength. Everybody understood this concept or not? Everybody understood this? Beta, what you have to remember? The colors you have to remember. I cannot help in that. And there are just few colors, but you can definitely, I just told you the complementary color idea. If you even remember the light absorbed, you can definitely just do the color of the entity on your own, because they are the complementary colors. You don't have to remember the wavelength at all, but the color of the compounds, not that necessary, but if you have time, then you can do it. Okay, next let's move on to this. I just told you that the basic condition for any element to show color of the coordination compound is that there should be presence of ligand. If there is no ligand, then there will be no d orbital splitting, there will be no dd transition, and hence no color. Hence ligand is essential for the compound to show color. Okay, for example, if I heat this, if I heat the violet color titanium H2O6 complex, what will happen? All the H2O will get removed, and hence because the ligand is removed, the compound is colorless now. It was violet, now it has become colorless. Similarly, on heating CuSO4.5H2O, you are removing all the H2O, hence white colored compound is remaining. Therefore, the color was due to the ligand, which is H2O. Only ligands can give color. The ligand is removed, the compound becomes colorless compound. Everybody understood this? Okay. Next, isomerism. We are here. People are screaming, ma'am, are we doing isomerism? When are we doing isomerism? So here, see, isomerism is here. So isomers, what are isomers, bacha? These are those compounds which have the same chemical formula but a different arrangement of atoms, right? The chemical formula is same, but the arrangement is different. Those are called isomers. There are two types of isomers, structural and stereo. Everybody can see on your screen. And we are going to deal with one by one. What are structural isomers? Structural isomers are which have the same formula but different bonds. The bonds are different. ठीक है? Bond is different. The connectivity can be different, but the chemical formula remains the same. These are of these following types: ionization, hydrate or solvate isomerism, linkage isomerism, and coordination. Let's see them by example. Example of ionization isomerism is here. Ionization means what? That the ionization sphere or the counter ion and one of the ligand can interchange between each other, right? So for example, here Br was there, Br was outside, sulfate was inside. Now in the next isomer, what I've done, I've taken sulfate outside and Br inside. So what I've done, I've just exchanged the counter ion with the ligand. So this kind of isomerism is called ionization isomerism. Why? Because the ionizing ion I am changing. And how can you detect the presence of Br? By using AgNO3, because then it precipitates as AgBr, yellow PPT, right? And the next is for the sulfate, you can use BaCl2, where it precipitates as white precipitate of BaSO4. Everybody understood this? Next isomerism is your hydrate isomerism or solvate. This is again a type of ionization isomer, but here the exchange happens with just one specific ligand, which is your H2O, aqua ligand. Right? Here again with the counter ions I'm exchanging. Here for example the counter ion is Cl, chlorine, and I'm exchanging it with H2O. Right? And here the one H2O goes out and one chlorine comes in. So again, what I'm doing is similar as ionization isomer. I'm exchanging the ligand with the counter ion, but here one of the ligand is actually water. Hence it is called hydrate isomerism or solvate isomerism, and therefore they have different colors as we change the ligand. As I told you, ligands give the color to the complex. This one has a violet color, the other one has a green color. Next is linkage isomerism. When we read about ambidentate ligands, I taught you about linkage isomerism, right? What was linkage isomerism? For example, look at this complex. This cobalt is attached with 5 ammonia and the next is it attached with a NO2 ligand. Okay? Here the connectivity to the cobalt is through nitrogen, while in the other case the connectivity through cobalt is through oxygen. Can you see? The chemical formula of both is the same, but the connectivity is different of attachment. So therefore, these kind of isomerism is called linkage isomerism. It is mostly shown by ambidentate ligands, right? Ambidentate ligands show linkage isomerism. Next is your coordination isomerism. What happens? That both the cation and the anion of your coordination complex here, bacha, will be a coordination complex. Okay, see, coordination complex as a cation, as an anion, and what is happening? Here you are interchanging the ligands with each other. Here the ammonia is here, the CN is here. In the next isomer, you exchange the CN with the cation and the ammonia with the anion. That is it. That is called the coordination isomerism. Next is the geometrical isomerism. Geometrical means what? This is the isomerism due to the different geometrical arrangement around the central metal atom. For example, the cis-trans isomerism. So the best example of geometrical, it means what? That the connectivity is same. For example, to this carbon, if OH is attached here and here one methyl group is attached, and similarly if the CH3 is here and the OH is here, what is happening, bacha? That the connectivity is same, right? To this carbon only one OH and one CH3 is attached, but their arrangement is different around the central metal atom. There are two types, cis and trans. Let's look at it. So these are shown by two kinds of complexes, square planar as well as octahedral complexes. What? Square planar as well as octahedral complexes. These are shown by, okay, and for square planar, who all show geometrical isomerism? Who do not show? First of all, square planar Ma4 do not show any geometrical isomerism. Why? What is the structure of a square planar complex? For example, it is PTCl4. This is a kind of Ma4 kind of square planar complex. Can you see all the atoms are same? Will it show any isomerism? No. It has so much of symmetry. All the ions are same. Hence, this will not show any kind of geometrical isomerism. Similarly, Ma3b, which means you just interchange one of the chlorine with some other thing. This will again not show any geometrical isomerism. Okay, what will show? Ma2b2 type, Ma2bc type, and MABCD type will show geometrical isomerism. We're going to see each and the following examples. Okay, let's look at Ma2b2 type of example, which is PTNH3 whole twice and Cl2. Okay, can you see that there is cisplatin means what? That both the chlorine and both the ammonia are on the same side, but trans means what? That the chlorine or the ammonia are on the opposite side to each other. If they're on the same side, it is cisplatin. If they're on the opposite side, it is transplatin. Everybody is understanding this? Can everybody see this structure? Okay. Next is your Ma2BC type. So what is happening in the Ma2BC type, bacha? Ma2 means two of the ligands are same and the other two are different. Now you will tell me, ma'am, in this case, how can we determine which is cis and which is trans? Which is extremely easy. So the two ligands which are same, for example NH3, if they are on the same side, then it is a cis isomer. But if they are on the different side, see for example, look at here. Here the NH3 is here. In the other place, the NH3 is right opposite to it. Right opposite to it. Hence, this is a trans isomer and that one is a cis isomer. Everybody understood this? Everybody understood this? Okay? Now next is the MABCD type of isomerism. What kind of isomerism will this show, ma'am? How will I know which is cis, which is trans? So I'm going to help you out over here. This kind is asked in exams so many times. For example, again, PT. To the PT, all different groups are attached. But look at those groups which are somewhat similar. Can you see that Cl and Br are actually quite similar groups because they have the quite similar structures, right? Chlorine and bromine are quite similar. So I can treat them as similar kind of ligands. So when they are on the same side, for example, in this case, Cl and Br are on the same side. This is a cis isomer. Again, here what is happening? Cl and Br on the same side. You can keep changing this position. The pyridines one time was here, the other time was here, one time was here, another time was here. But here, when the Cl and Br, which is the similar kind of ligands, are on the opposite side, then these will form the trans-geometrical isomerism. So we have discussed square planar geometrical isomerism. Let us go back. Let us go to the octahedral complexes. Now for the octahedral geometrical isomerism, which will not show any geometrical isomerism. Obviously, when all the ligands are same, what kind of isomerism that can show? So Ma6 will not show any isomer. Then Ma5, you just change one of the ligands. Again, you cannot show any kind of isomerism. This will also not show any geometrical isomerism. But Ma4B2 will show, Ma2BB2. BB2 bacha means what? That here the ligand is bacha what? The ligand is a bidentate ligand. Correct? A bidentate ligand is written as a BB2 and next is the Ma3B3. All these will show geometrical isomer. Let us see one by one. For example, Ma4B2 type. In Ma4B2, this kind of structure can be there when the Cl are right next to each other. When two similar compounds, when two same ligands are on the same side. Can you see this is on the right together each other, then this is called a cis isomer. But when the Cl, the bonds, what is happening? When the angle between the two similar atoms is 180 degree, it is called a trans isomer. This is the best way to identify the isomerism. When the angle is 180 degree, these are called the trans isomer. Okay. Next is Ma2BB2 type. I just told you BB2 means what? BB2 means a bidentate ligand. Now here, what will be cis and what will be trans? Can you see here that the angle between, in the trans, what is happening? I just told you that the angle between the two similar ligands, whether it is to chlorine or whether it is to ethylene diamine, the angle between them is 180 degree. The angle between two similar is 180, hence it is a trans isomer. This is the best way to identify. And the cis isomer is when the angle will not be 180 degree. It's going to be a cis isomer. Simple, easy peasy. Next is the Ma3B3 type. So what happens in Ma3B3 type of geometrical isomerism? Look at this compound. CONH3 whole thrice and NO2 whole thrice. Look at these compounds. Okay, what is happening over here? BB means bidentate. Yes, any bidentate compound that is there. Now here three ligands are different. Sorry, three ligands are same and the other three ligands are same. Now here there will not be any cis or trans. This is a very specific type of isomerism and this is asked every year. This is a favorite question of the examiner. Ma3B3 type will always be asked. Okay, so these, even though they are geometrical isomers, but they do not show cis or trans. Rather, they show a facial isomer, FAC, or the meridional isomer. Okay? Again, the best way to identify which is cis and which is facial and which is meridional. In meridional, bacha, what will happen? two of the similar ligands will be again at 180 degree to each other. Can you see? And here in the facial, none of the similar ligands are 180 degree to each other. So MER is actually, you can consider, just for your memory, you can consider it is a form of trans isomer. Okay? It is not true. Do not write anywhere in the exam. This is just me telling you a trick. Meridional is a kind of trans isomerism where two of the similar ligands are at 180 degree to each other. This is a best way to identify meridional and facial isomerism. Okay? Yes, they show meridional and facial isomerism. This is a very important favorite question of every examiner. So please focus on these kind of isomerism. The last isomerism, we are about to complete the chapter, which is your optical isomerism. What happens in optical, bacha? The complexes which have same physical and chemical properties but differ in their action towards the PPL light are called as optical isomers, and the phenomena is called optical isomerism. PPL is what? The plane polarized light. Whether it rotates the plane polarized light in the left direction or the right direction, that actually gives us, tells us about the optical isomerism. For example, in geometrical, what was happening? See, in the structural isomerism, the bonding was different, right? The connectivity was different. In the geometrical isomerism, the connectivity was same, but the arrangement in space was different. In optical isomer, what happened? It can only be determined by the PPL light. So that is the function of optical isomerism. And optical isomerism is shown by only and only optically active compounds, which are those which are non-superimposable mirror images of each other, which means to the central metal atom, all of the ligands attached should be different, number first condition, and they should have no symmetry in them, and they should form non-superimposable images of each other. Okay, and optically active complex is asymmetric in nature and not divisible into two identical halves. Okay, now they can be either dextro-rotatory or levo-rotatory. If it rotates the PPL light in right direction, it is dextro. If it rotates in left direction, it is levo-rotatory. Okay, and the D and L isomers or compounds are called the enantiomers. Again, optical isomerism. One of the classification is enantiomers. What is enantiomer? Enantiomer is the mirror image of the compound. Okay, what is enantiomer? It is the mirror image of the compound. For example, here, look at this. What is that? This is PTEN thrice. PTEN thrice. This is the complex that we have. So PTEN thrice, and what form is it? This is the cis form of PTEN thrice. Okay, which forms two forms, D form and L form, which are called the enantiomers, which are the mirror images of each other. Next is optical isomerism is shown by tetrahedral complexes and octahedral complexes. Remember this, right? Geometrical isomerism is shown by octahedral plus square planar complexes. Optical isomerism is shown by octahedral and tetrahedral complexes. Now, why square planar do not show any optical isomerism? Because bacha, in square planar complexes, can you see there is a plane of symmetry present? So anywhere if there is any symmetry present, those compounds will not be optically active, and hence they will not show any kind of optical isomerism. Is this thing clear to you guys? Now for tetrahedral complex, because all the bonds are just haywire, and here the mirror image can exist, and for tetrahedral only and only MABCD, where all the four ligands are totally different to each other, will show optical isomerism, just like how you study in your organic chemistry. Correct? Next is your, for octahedral complexes, only cis forms. Only for octahedral. For the tetrahedral, only MABCD types show the optical isomerism. And for octahedral, only the cis forms show the optical isomerism. And what kind? MA2, B2, C2 type, MABCD, EF type, MAA3 type, MAA2, AA2. AA, whenever two written just like this, it means it is they are talking about a bidentate ligand. MAA, B2, C2 type, all of these will show, all of their cis forms will show optical isomerism. For example, in Ma2B2C2 type, can everybody see this? In Ma2B2C type, everybody look at this. What is happening? What is happening? We have formed a cis isomer where two chlorine atoms are together, the two NH3 atoms are together, the pyridine atoms are together. It is a cis isomer, and this will form a D as well as a L isomer mirror image. Okay? And but the D and L, you cannot tell by looking at the molecule which is D and which is L, which is a small d, which is a small l. This is only can be possible to know after experiment. Okay? You cannot just look at the molecule, because you can also name this as the L isomer and this as the D isomer. It doesn't matter. One of them will be D, one of them will be L. That is it. Okay? Next is the MABCDEF type, where all things are different. If all the things are different, of course they can form a mirror image to each other, and hence they will show optical isomerism. Next is the Ma3 type. For example, ethylene diamine. The cis form of it. Cis form means what? None of them should be. Cis form looks like this of COEN3 type, and the cis form actually shows enantiomers. It forms D and L forms, which are called what? Bacha? These both are enantiomers. Okay. Next is the MAA2B2 type. In the MAA2B2 type, bacha, what is happening? Again, the cis form, where the two En which are the similar, the two Cl. Okay, let's look at Cl. They are at cis to each other, and the cis form again forms a mirror image. Okay, and again your MAAB2C2 type. Can you see that here the two Cl are together, the two ammonia are together, right? And the En is here. So here this is again a cis form. This again forms a mirror image just like this. So here we have ended the entire ordination chemistry. If you have stayed with me till the end, bacha, congratulations to you. You've completed the entire organic chemistry. There is not, you can go and attempt the PYQs on your own. I would have done it today, but right now I think we're running out of time. It's already been approximately 3 hours, and today I have spoken for about 7 hours today. So I'm also a bit tired, but we're going to keep another session for the PYQs. Doesn't matter. We have done the entire theory part. And if some parts are still remaining, few topics, if you feel, ma'am, I don't know that, you haven't taught us that topic remains. So you can just let me know in the comment section whenever, and we're going to take that class for you guys. Okay, and if you want the notes for this session, if you liked my session, please like it. And if you want the notes, you can join the Telegram channel, which is down in the link below. And on that Telegram channel, you will be shared a link. Okay? On that link, you just need to log in onto the Vedantu website, and after you log in with either your name or your email ID, after logging into that, you can get access to the notes. Okay? So there's just one extra step added, but that's just to keep a data entry for us guys to know how much you guys are actually using the platform. Okay? Thank you so much for attending. Beta, you tell me what chapter you want to learn next. And also tell me in the comment section. This chat will get lost. Okay, nobody will get to know what you said in the live chat box. After the video ends, comment in the comment section and let me know what chapter you want me to take next. What feedback you have for me. And what else do you expect out of me from this channel? Do you like me? Do you not like me? Or do you like longer sessions? Do you want to have shorter sessions? Or you want to do PYQs or just solve questions? Whatever feedback you have, just give it to me, but in the comment section. Also, please like the video, subscribe to the channel if you're not subscribed yet. And that's how we can talk to each other, right? And also share it with your friends if you like it, because this in 3 hours, no one will do justice to coordination chemistry like how I've done and made it concise into 3 hours lecture. I'm so proud of myself. Thank you so much. Thank you for attending the class. Bye-bye.